Oh,
Okay, there we go.
yeah.
Test, test, test one, test two. Hello?
I mean, hopefully it's not enough. You wouldn't mind actually wearing the jacket because it has like that thing that sticks out slightly closer to your mouth. Right?
Wait, this seems working. Is this good enough?
Actually, yeah, that does sound. Does that? Yeah, that sounds loud enough. Actually, yeah, you're fine. Okay, so we'll just.
Maybe it's the direction of the microphone.
I think it is loud enough. I think it's just.
Test one, test two.
Yeah. All right, so just go and just take the thing real quick.
Okay, I'd like to welcome everyone to this session. We have 3 talks. The second one is going to be remote. And the first talk is compiling with generating functions. And how do you pronounce your first name? I'm sorry, I should have checked. Jialin Li will give the talk. Thank you.
Hello, everyone. This is Jialin from University of Waterloo. This is a joint work with Izhou. The title of our paper is Compiling with Generating Functions. We present a new approach to scaling exact inference in Bayesian probabilistic programming using probability generating functions as a compilation target. Now, here is an example of a probabilistic program. The function Poisson packet arrival models network traffic, where packets arrive accordingly to a Poisson distribution, which is a standard assumption in traffic modeling. It first samples X from a Poisson distribution with parameter lambda. Then, the loop sum expression uses X as the number of loop iterations, computing the sum of the loop body. The loop body calls forward packet, which returns 1 if a packet reaches the destination and 0 otherwise. We use flip theta as shorthand for sample Bernoulli with parameter theta. This forward packet function models a 2x2 network topology and the probabilistic behavior of the router network, where each link has a 10% chance of failure. So the loop sum expression simulates forwarding all X packets through this network topology and computes the total number of packets that were successfully transmitted. Note that the forward packet function may be arbitrarily complex. Say it could be a 3x3 grid or a n/m grid. Programs like this are challenging for current PPLs. For example, DICE is a state-of-art PPL. It compiles probabilistic programs to binary decision diagrams, BDDs, for exact inference. Jennifer is another state-of-art PPL. It's imperative, and it compiles to generating functions for exact inference. DICE cannot handle the infinite support Poisson distribution and does not support loops. Jennifer supports Poisson distributions, but it struggles to scale to complex networks. And Jennifer does not support loops neither. Sampling-based methods, including importance sampling and Hamiltonian Monte Carlo, they are used in probabilistic programming languages like Pyro and Stan. These methods struggled on this inference problem. The cause is the high-dimensional discrete structure and its non-differentiability. We implement our approach in a probabilistic programming system called Ginny. Ginny is a functional PPL. The central component of Ginny is the compilation from PIL to DIL. PIL, probabilistic intermediate language, is a functional probabilistic programming language, and its only base type is the natural numbers. DIL, deterministic intermediate language, is the target language we use to specify generating functions, where the base type is the real numbers. You can think of DIL as a standard expression language, first order simply typed lambda calculus with real numbers and product types. Ginny is expressive since it supports finite and infinite support discrete distributions, continuous priors, Bayesian observations, and a restricted form of unbounded loops. Ginny is scalable since it effectively exploits independence and determinism in program structures, enable compiler optimizations that reduce the dimension of generating functions and derivative computations. Ginny is accurate since it's doing exact inference. Before we dive into the details of Ginny, let's first go through the basic ideas of probabilistic generating functions real quick. For a random variable x supported on the natural numbers, its probability generating function is defined as the expectation of the formal parameter lowercase x to the power of random variable uppercase x, that is a weighted sum where the weights are probabilities. For example, if x is a Bernoulli random variable with parameter 0.1, the generating function is a polynomial with 2 items where the coefficients are probabilities. Here, the lowercase x, a real number, is the formal parameter, while the uppercase x in the exponent, a natural number, is the random variable. From a generating function, we can recover probability masses and expectation by taking derivatives. For example, the probability of x being 0 and 1 can be computed by taking the 0th order and 1st order derivative at 0. So far, generating functions may not seem that useful. But in fact, many common infinite support discrete distributions has closed form generating functions. For example, the geometric distribution, the Poisson distribution, and common continuous distributions also have generating functions, such as the exponential distribution and the Gaussian distribution. By choosing generating functions as compilation target, a PPL can represent these distributions, making it more expressive. To represent probabilistic programs as generating functions, the concept of generating functions need to be generalized from the single variable case to the multivariant case. A multivariant generating function serves as a container for all in-scope random variables. When a variable xi goes out of scope, we remove it from the typing context and marginalize it from the generating function by set xi to 1, yielding the generating function of the remaining dimensions. Generating functions also support affine arithmetic expressions, and based on this, we can derive that for two independent random variables x and y, their generating function of their sum is the product of their generating functions. Next, I will show how Genie compiles PLL programs to generating functions with simple examples. For arithmetic expressions, for example, a random variable z defined as the sum of x and y, where x and y are sampled from Bernoulli 0.1. The generating function of z is the product of their generating function evaluated at z. At this point, you can verify that the three coefficients are the probability of 0 being 0, 1, and 2. And note that in Genie, the representation remained factorized. In Genie, we designed and supported a restricted form of unbounded loop. Here, x is a random variable that determines the number of loop iterations, and forward packet denotes a distribution together with its generating function of random variable y. Let that be the random variable representing the sum of x many independent samples of y. By previously shown equation, the generating function of z is gy of z raised to the power of x, but since x itself is a random variable, we need to marginalize it out. So after a few rewrites, the generating function of z simplifies to the composition of the generating function of x and y. Genie is the first PPL that is able to express and exactly solve this traffic analysis model thanks to this loop sum construct. Genie achieves good scalability thanks to compiler optimizations and the nice properties of generating functions. Let's now see how these techniques work in practice. Genie exploits independence and determinism in programs and keep generating functions factorized. Consider this PLL program on the left. It computes Sn as the sum of x1 through xn. The program returns 1 if Sn is greater than 0 and returns 0 otherwise. In other sense, it represents the disjunction of n Bernoulli random variables. We start from the generating function on the first line. It is the trivial generating function for the empty typing context. It takes no arguments. Each line of the PLL program transfers a generating function to another generating function with one additional parameter. In this case, the first line of the PLL program transforms the trivial generating function into a generating function that takes x1 as input. And then the second line of PLL program further transforms it into a generating function, takes x1 and s1 as input. Up to this point, the random variable x2 is independent of x1 and s1. So the new generating function is the product of the previous one and a factor associated with x2. In other words, it remains factorized. Then after a few steps, let's pause before the if then else and look at the generating function closely. It takes 2n parameters as input. It's factorized. It's a product of n factors. Each factor contains on operands. So evaluating this factorized generating function requires on squared time. If Jenny does not exploit independence and does not keep generating functions factorized, the resulting generating function would expand into exponentially many terms. And evaluating the expanded generating function requires exponential time. Factorization reduces the complexity from exponential to quadratic. This is good, but not good enough. A key optimization in Jenny compiler is the marginalization of variables when they are no longer alive. Optimizations reduces the input size of intermediate GF expressions created during the compilation, which can lead to saving in time and space during inference. We start from the generating function for the empty context again. But here we realize this line is the last use of x1, which means that we don't need x1 anymore. So we could marginalize x1 out from this generating function by set x1 to 1, yielding the generating function of only one random variable, s1. x2 is still alive here because it's used in the next line. s1 and x2 expires after s2 is defined. So here we could marginalize s1 and x2 out. Importantly, these substitutions are carried out in exec when the variable's liveness ends. After a few steps, let's pause again before the if then else. Now this generating function only takes one argument. Since all dead variables are already being marginalized out, let's look at this generating function closely. With the expired variable marginalized earlier, the generating function at this point takes only one argument and can be evaluated more efficiently in linear time thanks to the factorized structure. By contrast, if the marginalization was delayed until the end of the program, the previously shown generating function would be generated. It takes two arguments as input, and evaluating this generating function requires on squared time. So early marginalization further reduces the complexity from quadratic to linear. I think this is good enough, and this is the best we can do in theory. One of Jennifer's main performance bottleneck is taking derivatives. But by definition, the probability of a variable being non-zero is a sum of derivatives. The sum may be finite or infinite, and evaluating derivatives is computationally hard. While in Jenny, there's no need for differentiation when testing if a variable is non-zero. We note a perhaps obvious fact for a random variable x supported on the natural numbers. The probability mass of non-zero event can be directly read off from its generating function as follows without differentiation. This optimization seems simple, but it's super effective. It allows Jenny to avoid differentiation for a large class of programs. Basically, all the programs can be expressed by this. For example, consider the compilation of the if expression in the previous example. There, the generating function GSN is the symbolic representation of the program execution before the if statement. Jenny transforms it into two GF expressions with constraints GSN to the case where Sn is true and false, respectively. The else branch GF is obtained by setting Sn to 0, while the then branch GF is obtained by subtraction. Avoid differentiation is not required here. The final generating function, g of z, is the sum of transformed generating function from the then branch and the else branch, respectively. G of z describes the probability distribution of the program's return state. Here it tells us the probability of returning 0 is the product of theta 1, theta 2, all the way up to theta n. With this background on generating functions and core ideas of Jenny established, we are now ready to discuss the formalism of our compiler. Our compiler correctness theorem can be viewed as a commuting diagram. PLL, the source language, a functional PPL. DLL is the target language, a deterministic expression language that describes generating functions. The blue arrow from PLL to DLL represents GF compilation. We can view GF compilation as symbolic execution of a PLL program and a PLL program as transformers between generating functions. The orange line from PLL to its denotational semantics, the denotational domain is measure transformers. We use a measure transformer view to define the denotational semantics and the GF transformer view to define the GF compilation. The payoff is a tight correspondence between the denotational semantics and GF compilation. This tight correspondence makes the correctness of the compiler almost self-evident. Since we work in a functional setting, which improves the modularity but complicates the GF compilation and the formalism, we introduce a generalized notion of generating functions. And generalized GFs operates on semantic substitutions for typing context rather than fixed size vectors. This black arrow sends measures to generalized generating functions. DLL is mostly a standard expression language, so its denotational semantics is also standard. The compiler's correctness theorem says that GF compilation preserves measure semantics. In other words, this diagram commutes. We evaluated Jenny on a set of exact inference benchmarks. First one, the grid network. It's from the Problog paper computing the probability that a packet from the top left router reaches the bottom right router. We consider two variants, probabilistic link failures and probabilistic router failures. Both plots suggest that the runtime of dice grows exponentially in the square of the grid side lengths, while Jenny grows exponentially only in the side lengths, demonstrating better scalability than both dice and Problog. Let's back to our very first motivating example, Poisson packet arrival. This benchmark exercises two key features of Jenny: infinite support distributions and the loop sum constructor. Because existing tools for exact inference cannot handle this program, we compare against Pyro's importance sampling. In this plot, we show the L1 distance between the true posterior expectation and the estimated expectation from the importance sampling as time progresses. While Pyro eventually converges, but it only begins to show signs of convergence after 10 minutes. In contrast, Jenny swiftly produced the exact solution. To our best knowledge, Jenny is the first system can automatically derive exact solutions for this class of probabilistic programs. DICE has been applied to probabilistic model checking, where it is shown to outperform state-of-art model checkers such as Storm on some benchmarks. We also compare DICE and Jenny on such verification task called weather factory. The task is parameterized by time horizon h and the number of factories n. The left diagram shows how running time scales with time horizon h. DICE exhibit superlinear scaling, while Jenny shows linear scaling. This means that Jenny can exploit Markov property, a type of independent structure, better. Ooh. The right diagram shows how the running time scales with the number of factories n, and Jenny scales beyond the limit of DICE and Storm. The result identifies a promising application of Jenny. It's potentially beneficial to include Jenny in the back end of a probabilistic model checking tool. We also compare Jenny against DICE and Jennifer on single marginal inference task over Bayesian networks. This table shows that Jenny and DICE are comparable on basic networks such as Haber2 and PIGS, which contains thousands of parameters, but DICE is faster on larger ones. Jennifer times out on all benchmarks. By contrast, Jenny can compute exact solutions within 5 minutes for all 7 basic networks in this table. Jenny and DICE have complementary strengths. On some inference tasks that motivated the use of DICE, Jenny may scale surprisingly well, where DICE scales superlinearly. Jenny may scale linearly, and in cases where they are both scales exponentially, Jenny may do so with a smaller base. These problems also involve substantial independence and determinism. But DICE may outperform Jenny on some other inference problems, particularly those ones with large, dense, conditional probability tables. Handling large conditional probability tables well requires extracting the local structure implicitly presented in the tabular representation. And binary decision diagram compilation in DICE largely automates this process. We expect future work to investigate the strengths of these inference methods more thoroughly. To conclude, we designed a PPL compiler with an interesting compilation target, namely generating functions. We demonstrated that with appropriate design choices and optimizations, a GF-based PPL can scale surprisingly well on some difficult inference problem. And in addition, this compiler is proven correct and available on GitHub. Thanks.
So we have time for a couple of questions.
I would say it's the right time of the pipeline because the PIL program, we don't really change the PIL program. And we apply a program analysis on the PIL program. So we know exactly the time where each PIL variable expires. That's why in the compilation target, we kind of like delete it from the memory. So,
Got it. Cool. All right, thank you.
Thanks.
Hello, Matthias here. We are using, like ages ago at Bloomberg, we were having a little language for describing probabilistic programs, but what we were interested in was payoffs for financial contracts. And so the interesting thing that we did is I can't just answer the question. So basically, use the techniques you had to simplify our programs, but then at the end we ran like a Monte Carlo. Are you also only interested in like precise, like symbolic computations, or also interested in doing it approximately, maybe doing better than the other system for stuff? Just run Monte Carlo or whatever. You only want the precise answer, the exact answer.
So is your question like, is Jenny only do exact inference?
Or are you also interested in running approximations, but maybe running them better than before?
I didn't really get the question. Is your question like, is Jenny only deal with exact inference?
Yeah,
the answer is yes. Jenny is a very, it's a prototype. We only solve this problem in this paper. And in future, we could imagine if there's a syntax structure that controls the inference method applied to sub-expressions, so we can mix different inference methods. Like this part solved by exact solution inference, that part solved by approximate inference. I think that would be an interesting future direction.
Okay. All right. Thank you. We should probably wrap up and thank the speaker again, please. So I'm not quite sure how this is going to work, but the next talk is going to be virtual. So do we know who? may need to swap the schedule around because the other speaker seems to not be available.
So the speaker just isn't here?
Yeah, it's
I mean, can we switch up the third speaker if you want?
Okay.
I'm telling the AV folks that. Yeah, sure.
We may need to switch the schedule around here a little bit because the remote talk doesn't seem to be quite ready.
Could you try speaking into that?
Okay. I mean, I should speak straight ahead, I guess, which means that this is not close enough, or maybe it should be further up. I don't know.
Try that now.
Okay, trying. Okay.
Okay, so we're going to dynamically switch the schedule around here just to make sure that we make progress. And so we'll be having the third talk on domain-specific tensor languages. And Patrick Janssen is going to give the talk, and then hopefully we'll have made contact with the speaker for the second talk by the time this is done. Thank you. Oh, okay, wait.
Right. Yeah, sure.
Okay, so, all right, so maybe we'll undo. It's a good thing we're functional programmers. It's easy to undo things. Okay, great.
Are you guys ready? Can I start? So, what's happening?
All right, so I'll introduce this talk while we're figuring out the AV stuff. If I can.
Can you see my screen? If I switch to the slides, is it there?
Okay, so Artems is going to give this talk, and it's correctness meets performance, and then there's some discussion about Agda as well in the title. Yes,
Can you
Agda
hear
to
me, guys?
Plutarch.
Hello? Hello? Hey, people. Hey. Can you hear me? Hello? Guys, I don't know if you can hear me or see my slides, and I'm not sure whether I should do anything now. Hello? Hello?
Can you hear me?
Yes, I can hear you. Yes.
Okay, so we're having a little bit of trouble setting. Do you have a way of increasing the gain on your mic?
I can make my mic louder. Is this better?
Yeah, sorry, we can sort of hear you, but only just barely.
Let me see what I can do, but I'm at maximum of my volume, so let me see what I can do. No, I'm at the maximum.
Just
I'm not sure what I
they're
can.
trying to sort it out. Just give us a minute.
Okay. Okay, sure.
Can you say something?
Yeah. Hello. 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 Hello.
All right.
Hello.
Can you say something again?
Hello. Hello.
All right,
Hello.
that's
Hello.
good. That's good.
Okay.
All right, so I've actually already introduced you. Can you get the slides back?
Sure. Sure. Can you see my screen so I can start my
Yes.
slides?
Yes, you can see your
And
slides.
my slides are visible now. Okay. Good.
All
So
right.
then I have 20 minutes to
Okay.
go through this. Can I start?
Yes, please start.
Okay, thank you. All right, so I'm Artem. I'm going to present this work, Corrected Speed Performance. I'm from the University of Southampton, and this is a joint work with Troels Henriksen, who's from the University of Copenhagen. Let me start with a little bit of motivation. So we are looking into numerical applications, and we observe two kinds of numerical applications that are out there. First kind is the ones that are written in low-level languages like C or Fortran, or maybe in Python with wrappers around high-performance libraries. They typically run very fast, but they have very poor correctness guarantees, specifically if we talk about formal correctness. It's very difficult to formally tell that they do things that they're supposed to. The other kind is ones that are written in, say, theorem proofs like Lean, Rock, or Agda. They specify very nice data structures, and they can have even wide complexity like AVL trees, but they rarely designed to run efficiently. So the question that we're asking ourselves is how to combine these two kinds in a single one, right? So can we envision a way to write numerical applications, have some nice correctness guarantees of our choice, and that still run efficiently? And when people hear this question, the immediate reaction is typically, oh, well, sure, but we need a single language. And the vision that we're trying to put forward in this research is that, well, maybe single language is all good if it exists, but maybe in the meantime, it is better to follow the following compromise. You want to combine a dependently typed proof assistant, just a proof assistant, to do correctness engineering in, and high performance language to actually generate efficient code. And maybe for now, it could be a good compromise if these things would work in collaboration. Okay? In particular, we want to look into combination and Futhark. So ACT is the independently typed theorem proof. We want to write specifications about our specifications in Agda, then generate some code to Futhark, which is an performance trained language that is famous for generating very efficient code, runs on GPUs, right? So we take all kinds of low-level details that you typically think about, like parallelism, word groups, all kinds of stuff. In order to test whether this idea is realistic or not, we're implementing a canonical convolutional neural network. We implement automatic differentiation for it to perform some training. We extract the code program, give it to Futhark, and try to run it and see how it works. Okay. In order to get there, so and this is actually the paper. So first we define a theory, and if we follow the lessons that we learned from EPL, that if we want to define numerical applications, it's to do this by defining a bunch of rank polymorphic combinators. Rank polymorphic means we extract over the number of dimensions in the arrays, and then if you put them, if you define the composition of these combinators, you end up with a very general a numerical application. So we do this for the CNN. This doesn't give us a way to analyze the expressions, analyze the programs. In order to do this, we're going to define a DSL. It's going to be a deeply embedded DSL. And in this DSL, well, first of all, we're going to define some conveniences like high order abstract style wrappers. You can write nice programs in it, do not fight the redundancies. Then you can define automatic differentiation as a function from E3. So, which means that we could immediately high order differentiation if we want to. Then we define and prove that it is semantic preserving. And we need the optimizer to get rid of certain artifacts that are introduced by automatic differentiation that don't necessarily perform very nicely. Then we extract the Futhark, and then we see how. I won't be able to cover all these details, all these things in the talk. I'm only going to make a high-level overview. So I invite you to read the paper for actually understanding the details in case you're interested. So, a high-level overview. Let's start with specifying what exactly is this example. So we're looking into a convolutional neural network for digit recognition. That's trained on SSM data. It is basically a lot of convolutional neural network. This is very well understood example that has been implemented many times. And among other things, it has been implemented in array languages. For this is the code that you see in the array languages. It doesn't matter what it says, but the point here is all of these functions are implemented as array expressions. So SAC is not specifically designed to write networks. It's just a general purpose array language. The formulation of the neural network is very compact, and it runs quite efficiently. So the problem with this is that SAC as a high performance language doesn't give correctness guarantees. So it gives you like C-like properties, but not really. And it didn't do automatic differentiation. So everything there was implemented manually. So we want to take the inspiration from this work and bring it to the kind of theory. So in order to do this, we have to define array theory. We have to define arrays. And the key idea of representation of arrays is a very kind of old functional mantra that you present your data as functions and as functions compose, right? And we do exactly this. Our arrays as functions values, and we take care of. We should be able to define combinators, because if you don't, then something loop nest around your code is not generic enough. Okay, so let's look at code. So this is our array. Let's go to kind of bottom up. So this is an array type. It's an array of shape S and element type X is a function from positions that are valid for the shape X into values of X. So what is the shape S? Shape S is a list of natural numbers. Your nil, this is your cons. And what are the valid indices for the given shape? It's a list of natural numbers where every element is where every element is less than in the shape. right? So it's a dependent type, so it's indexed by the shape, and fin n is a natural number that is bound by n, including n. Okay, so this definition by design is index safe. If you want to index your array, you have to guarantee that your index respects boundaries, and we have defined shape as a single object. So we can abstract over shapes easily and quite nicely. How does it? Okay, if you know containers, the Gauss form of a container, yes, yeah, right. But if you don't, then this is just what it means. So arrays are very rich structure, and they have all kinds of nice properties. For example, if we fix the shape S, then our S is an applicative functor and enjoy all the done with it. For example, define a constant array where all the values like a K combinator, map, which is just a map. We can define zip width, which is of a binary function for two argument arrays. And so both arrays are traversable, so plenty of things that make for just this function representation. Then we have array-specific combinators that come from the shape and non-trivial. So if we shape concatenation, then we can switch between an array of concatenated shape and a nested array of the respective. And we can go back and forth, and this looks a bit like monadic join, or think about some form of currying, but these views of array are basically morphic because our arrays are okay. Then let's look at more CNF-specific combinators, and let's look how in this framework a convolution is going to be defined. So in order to define a convolution, it is useful to define a notion of slide. First of all, let's make shortcuts of vectors, which are one-dimensional arrays. So the vector of length m is an array of iota is a singleton list. Indices into positions into shapes. Then we define this operation slide, which says if you have a vector of length m and you have an offset, I can select a vector of length 1 plus n starting from the offset m. And basically the simply just you add indices as you go, and that's your basic subvector. Okay, and then in order to define the convolution, all you do, you take the way that you convolve weights, and then you state array A as many times as you have inside of the array W. Every W you slide array set, you multiply these corresponding weights, and then you add together point-wise, right? This is your one-dimensional convolution. Okay, the details are not that good, but you can see that this definition is really straightforward. And the other nice thing that it's immediately generalized to rank n. So you can find it for n-dimensional arrays in pretty much the same style. You need to be able to slide dimensions. For this, you need to go from the summation of shapes. So you have to define sum of shapes point-wise. You have to define a successor of a shape, basically as one element in this, and then you can define an n-dimensional convolution. In pretty much the same way as one-dimensional. You have to update your slides to n dimensions. You have to update your to n dimensions. Right. If we define a bunch of more combinators, write down a specific convolutional neural network like this, right? Again, the details are not very details are not is a lot more sophisticated than what we've shown before, but you can see that this definition is by construction index safe. These combinations have some properties that I talk about, and we didn't have to write any proofs, right? And it looks very much like the code that I started in civil science. Okay, so far so good, but this is especially in Agda, so we can run it over the performance that we have. So we still need to do some stuff to get all of the structural, and that's where we introduce. And we're going to introduce the DSL intrinsic style. So we want to eliminate the possibility to write expressions inside of the DSL. So what are the expressions we're to deal with at all? And it turns out for specifically these numerical examples, it is good enough to assume that we're dealing with base or some imaginary real number. We have to talk about the point is that it's the same for all arrays, so we can avoid this entirely. So the values that we want in our language are either arrays of shape S or indices of shape S. This is it. We don't want anything else. Then we use a standard. There's a SNOC list of these ASs. We define the proof relevant dependent variables. And this is how our DSL looks like. So again, don't read the code too much. It is a small language, so we just have variables, constants, array constructors, summation, some predicate on indices, slide back slides, as you see, in order to implement convolution, some arithmetic, and most importantly, local net binding. This thing allows us to talk about sharing some computations between these expressions, well, between the expressions, because it is. Okay, so I'm going to skip the evaluation so we can evaluate the syntactic back into Agda expressions. So we can introduce these wrappers to explain this, and if we do all this, then something find a syntactic version neural network. It's an expression in E, and we have to redefine these combinators in E. But if we do this, we get basically this piece of syntax and interpret this and see that it basically act the expression we start. Okay, what do we do with the piece of syntax? Well, we want to do automatic differentiation. We do a reverse mode automatic differentiation. And the complication here is that we do this in this intrinsic settings. We have to take care of making sure that the shapes and all the variables are preserved. And the structure that makes it all work is this vector of arrays of a certain shape, right? So we want to compute derivatives for all the three variables in our code. So we take a context and we define environment that's indexed with two contexts. So environment gamma delta means that we have gamma many expressions in the context delta. And the types of these expressions, they correspond to the positions inside of gamma, right? It's typical trick in this intrinsic encoding. Then we do not care about indices, so we can throw away all indices because they do not contribute to, they never contribute to the computations. So we don't have to compute derivatives. And then the trick that we haven't seen, which is very useful, we do additionally to this, we say that the action structure we work with is this extended environment, which is defined either as a normal environment or a lead binding that all the expressions in the environment can see, right? So we can introduce lead bindings for the entire environment. This is the way that application can preserve the right amount of sharing. Okay. So here's the how AP looks like. Again, don't read the code too much. Basically, just get a general impression. So it's a function from an expression in E, a seed, and it's basically it computes updates of the environment, and you start with the environment that is full of zeros. So what is interesting about this code is it, it is defined in terms of updates on the entire array. So we never talk about actual elements as you typically do in gradients and fluids. So this code is kind of short. It is by construction terminating as because all the anchor functions terminating it. It is well scoped and it's well typed. It doesn't guarantee that this particular implementation computes the derivatives, as you call them, for calculus, you know, if you think about epsilons and deltas. But hopefully, again, it's good enough to take this as a specification because we can look at this and see whether it makes sense. It pretty much it follows the standard rules of differentiation that you can read in the book. Okay, I'm going to skip the optimizer. We can optimize and we can prove that each optimization preserves the semantics. It's standard. We do code generation, and let me talk a little bit about performance. So we code generate. We give it to this on the GPU, and so is that if you compare it with the TensorFlow, which is industrial strength machine learning framework, then for small sizes we're a bit faster. For large sizes, we're a bit slower. But the important bit is, look, we are in the same ballpark as the industrial strength framework. And we picked a very tough example to compete with because, I mean, it has been optimized to death, right? It's a hello world of TensorFlow. It basically, it is being mapped to specific hardware units of a GPU that we do. But the point is, look, this is, in my books, is good enough, right? Which means to me that the approach where you combine theory and performance language is a reasonable thing to do, right? So they could coexist, and here demonstrate that this is awesome. I think I should stop. I be able to accept your questions after the announcement. For PhD students in Southampton who would be interested in doing something in time theory and high performance computing, a section of both. If you want to talk about it, if you're interested, please. And now I'm happy to take your questions.
Okay, thank you. Since we got a bit of a late start, I think we probably have time for like one question. If someone has a, could you please use the mic?
Sorry, I almost don't hear you.
So my question is about rank polymorphism. So is it possible to let after shape inference with, let's call them shaped variables, and then we need to assume it's the smallest shape to satisfy the shape inference problem?
Sorry, can the chair repeat the question? I have troubles hearing what the question.
So for rank polymorphism, you have a shape inference problem.
I heard shape inference, but I don't quite understand.
So after shape inference, can you have shaped variables left over? And you need to assume that.
Can I have shape variables left? Sorry, can the chair repeat the question? I can hear the chair very well, but I can't hear the.
Hello, do you hear me better? Or maybe it's.
Oh yes, I can hear now. Yes.
Sorry.
Yeah.
So do you have a shape inference problem for the rank polymorphism that you offer, that where you solve shape constraints?
Right. Yeah, sure. Everything here is manually, so we don't have any magic. So I mean, you have to. We don't. Well, we do as much inference as Agda does. It has some local inference, but of course, if you have some crazy expressions in the shape that are symbolic, you have to make sure that they match. And in principle, you can find yourself in a situation that you will have to write proofs. But for the cases where the shapes are static, then typically it's enough of the information for the local inference to kick in and resolve this.
Do you have leftover shape variables where you need to guess the smallest shape at the end? Or you need to assume the smallest shape? Where
I'm
it
not
could be
sure what do you mean. Leftover variables. I mean, we're just doing unification. So I mean, the shapes are we don't have any subtyping or subshaping. So we have to unify on the shapes. And if you have different expressions that mean the same thing, then you have to introduce casting. So you have to
Thank you.
define a proof that they're the same. There is no automation in this bit.
Okay, thank you. Let's thank the speaker again.
Okay.
Okay, so we're switched back to real life here, and the last talk of the session is domain-specific tensor languages.
Yeah, let's see if this microphone is on. Yeah, okay, good. So, domain-specific tensor languages is the only thing that keeps you from lunch. Yeah. Tensor calculus in this setting is not what they talked about in the previous slide. It's something from 100 years ago. It's not TensorFlow, it's tensor calculus. So the thing that Einstein had to learn from mathematician friends to be able to express the curvature of space-time. And an example is this Riemann curvature tensor here. It's a symbol with some upper and lower indices, and it's defined as this 4-term expression, which uses derivatives and Christoffel symbols, which are in turn implemented in terms of derivatives and the metric, which is also a 4-term expression. So it's a big, annoying expression. And we will we have implemented 2 tensor DSLs embedded in Haskell, conversions between them and helper functions to then view these tensors in the Einstein index notation or as diagrams. And the sort of 1 minute version of the talk, if you're impatient, is this. So we have this Albert after Einstein and Roger after Penrose languages embedded in Haskell. And as a very small example, the Albert function example of t and u is a contraction of this lambda expression. And here I've abused Unicode a bit. So this is an upper I and this is a lower I. These are 2 different variables bound by the lambda. I write low I and high I in the actual code, but render it this way. And then t is applied to one of the i's, deriv is applied, to the other I and to u. And then we will look at later what this might mean. This is the kind of expression you write in Albert. And this can render itself then as the index notation, well, which is slightly shorter. The contraction here is sort of invisible, but the fact that an index is used twice, there is a convention in the Einstein index notation that if it's used up and below, then it means the summation, so that's the contraction. It can also render itself as a diagram. We will get back to the meaning of those diagrams later, but you can see that at least the t is connected to u in some way here. And you can otherwise run it on matrix representations of these tensors and get actual computation results, even though we only use symbolic expressions and real numbers in the examples we've done so far. In the paper, the sort of motivating example is to express the general relativity equation for the curvature of space-time, which is this equation actually, using this curvature tensor, the metric, and the energy matter, sort of energy momentum tensor. We'll not talk much about that, but a little example at the end. So the 5-minute version of the talk is the core contribution is this implementation. 2 DSLs, as I mentioned, Roger after Penrose, is based then on symmetric monoidal categories. And the other one is based on linear functions between ports. And this is now, even though tensors are about linear algebra, this is type linear functions between ports. So it's not about, so there are two ways the word linear appears in this paper and this talk. One is as type linear functions, where you can use the argument, where you have to use the argument exactly once, and the other is when you have linear transformations. And the types we'll get into later, but you can see that tensor embed is a function that goes from this, which is actually Roger, and to the other thing, which is an expression in Albert. So you can get from one to the other and back. And we'll get to the exact types later. Okay, so there are two main lessons learned if you want to sort of condense. So one is that you can use both a point-free calculus and lambda expressions. That's what these two views are. And why is this relevant? Well, point-free calculations are algebraically nice. You can do calculational proofs and so on, but try to do plumbing of variables when you have more than 2 or 3 involved. That's going to be very awkward to work without variables. On the other end, if you have lambda expressions, you can easily connect computations, name and reuse different sub-expressions and so on, well, implemented as ports here. But reasoning is always harder with name binding and so on. So as I said, we provide both, and it allows you to mix and match in the sense that you can have sub-expressions which are in Roger in an expression using Albert and the opposite. And it means that certain expressions can be more conveniently expressed. And then the underlying technique here is what was published in 2011 and based on a well-known isomorphism between symmetric monoidal categories and linear lambda calculus. Well, it wasn't well known for me when I started this work, but apparently it's well known. And this is the sort of nice underlying theory saying that if you have an arrow from A to B in some category Z, which is symmetric monoidal, you can translate that into a polymorphic function between a port of type A to a port of type B, and this is the linear function arrow. And this squiggly arrow is only for formatting. ZAB is what it would say in Haskell. So Z is a 2-parameter type constructor applied to A and B. And then the decode function is the opposite direction. It just takes one of these polymorphic functions and goes back. You can think of the R here as a scoping construct handling, a bit like the ST monad in Haskell and so on. And this paper adds several things, but when it comes to this technique, it's mainly adding a little more structure on the category side to get compact closed and additive categories. And then we encode such an arrow not as a function just from port of A to port of B, but we require the compact closed, meaning that you can sort of turn inputs to outputs, which hints at like quantum computing and so on. So the B star here, which is written dual B in the Haskell code, is the sort of way of making an input and output or the opposite. So then you take an input, you take an output, and you return some results. And similarly, the two functions are inverses here as well. So if you have such a polymorphic function, you can make it an arrow. Okay, that was the 5-minute version of the talk. Let's continue with lesson 2. Building a DSL with type classes is a useful technique, and I'm sure most have used this in different languages. So if you take a very simple example, if you want to write a numeric expression, like lit foo, for example, it's x plus x times y, and it has type num A constrained A to A to A. So for any type A, could be integers or floats or polynomials or some other mathematical type, you could have this as sort of your interface for a numeric expression DSL. And basically these expressions are then, if you just use these class methods, you get generic numeric expressions we could later instantiate to different types. And that's how we build up Roger, but it has a little more structure to it. So we start from the category type class, not our invention at all. We add symmetric monoidal operators. I will show types on the next slide. We require these, I guess the HOM set of this category to be additive, so you can add morphisms and scale them, and then we require it to be compact closed, so you can sort of take an arrow and turn it around in the other direction. And the expressions using only these operations are then Roger expressions, and those are the ones which can be translated into the linear lambda calculus version. Of course, if this would be an empty set of requirements, they would be very useless, but we have a few instances, like for matrices, diagrams, and pretty printing. So expanding a bit, the actual interface declarations for the class category, it's, again, as I mentioned, Z here in Haskell will be just written prefix. So ZAA, ZBC, ZAB, and ZAC. That's identity and composition. So the whole Roger language is a way of describing morphisms in some category. And the symmetric monoidal has, in addition to these operators, 5, 6 more. So tensor product is the most important one, where you basically put two wires in parallel, or two computations, two arrows in parallel. And then you can do some swapping, associations, and so on. And I mentioned additive, basically saying that we require the arrows, the home sets, to be additive, to add addition and scaling and a 0. So that's the structure. And I talked about diagrams. These are the key operators and how they are rendered. It's a bit fun because Jean-Philippe is really a Tesh and Haskell and everything hacker, so he implemented this thing. So the paper and the talk generates these figures automatically. So this syntax generates this, and this is generated from the type of this. I maybe specialize it to a monomorphic type just to illustrate. So composition, well, in the diagram form, it's pretty clear. You take some input port I, you thread it through T and U and go to J. Well, actually, what is input and what is output is not that important because you can then dualize it. The Einstein notation version has I and J as indices, but then also a K. And the fact that it appears both below and above means that it's implicitly summed over. So there's actually a contraction happening here. That's a sigma K over this. So it only has 2 free variables, and the third K is a bound variable. This is not Haskell notation. This is the Haskell notation or the Roger notation. The tensor product is, as I said before, running 2 computations in parallel. So I and J are inputs, K and L are the output ports, and T and U are sort of run independently here. Sigma, the swap, well, you just cross the wires, and associators, alpha, they take I and J close together here to M and N close together there. So it's sort of implementing associativity. And you can imagine if you want to have a large wire diagram, like something from the first keynote talk, it would be very inconvenient to write it in Roger, but you can generate that from the lambda expression version. Okay, getting slightly more concrete, how do we implement this vector space part in Haskell, where we have first an additive group, addition, 0, and negation, and then we add the scaling operator. So it's an infix operator taking a scalar on the left and a vector, and then scaling it up or down, or flipping it if it's negative. We haven't parameterized it on the type of scalars, but that could also be done. So S is some type, for example, real numbers. So if you want to be extra concrete, you could say S is real numbers, V is capital V being a 2-dimensional vector space with some basis vector, and as you know from linear algebra, we can then write any vector as some real number V1 scaling E1 plus some real number V2 scaling E2. So it means also if we later we can have a basis for the tensors, and we can write linear combinations of tensor expressions. So the category that's at least symbolically intended is the category of finite dimensional vector spaces as objects and linear transformations between them as arrows or morphisms. And these arrows are the tensors. So tensors are linear transformations between vector spaces, or often described as linear transformations between tensor products of vector spaces. So to be a little more concrete, the types here, A and B and C and so on, they are representing the index set of the basis. So if it's the unit type, it's a 1-dimensional vector space. So there is just one index vector. And what is that vector? Well, you usually call it 1. So the real numbers is a one-dimensional vector space over the real numbers. So any vector in that vector space can be written as a scalar times 1. A two-dimensional space we had in the previous slide, and if you want an example of a linear transformation, then we can take rotation by 90 degrees. And it can be represented as a matrix. Well, this I can just show quickly. If you have a vector space, you can also make a vector space of functions. You just lift everything and work on the return side. And then we can get the simplest examples of actual tensors. So as I mentioned, if you have the unit type, then it's basically real numbers. So what is a linear function from a real number to a real number? Well, linear function here means really linear algebra linear, so it's just multiply by a constant. So you can determine a scalar is isomorphic to a linear function from the one-dimensional to the one-dimensional space. And then a vector is 1 to v. A vector ether, a covector, is something from v to 1, and then a normal matrix or linear transformation would be v to v. These are usually described as tensors of order 0, 0, so 0 for the input, 0 for the output, 0, 1, 1, 0, and 1, 1. And you may notice this order here is a pair of the, you could say, the exponent of v on the left and the right. So how many v's are tensored together? So generally speaking, a tensor is usually v to the m arrow v to the n of order mn. So you can have like 3 things on the left and 5 things on the right if you want. And you can informally think of it as taking m vectors as inputs and producing n vectors as outputs. But it's not quite that, because that would indicate you have a Cartesian product. So you have like really the different vectors in your hand. But tensor product doesn't quite work that way. So if you have a basis for v and a basis for w, say 2-dimensional and 3-dimensional vector space, then the basis for the Cartesian product would be 6-dimensional, 2 times 3, while the Cartesian product would be the sum, 2 plus 3, a 5-dimensional space. So you can also do the tensor product on the value level. So you can take 2 vectors or 2 tensors and tensor them together. It's a little bit like a pair, but you can move constants between them. So if you have a constant scaled v tensor w, it's the same as v tensor c scale w. That means that if you tensor 2 things together, you can't get the vectors back out again. They've sort of been entangled together here. And it's a bit like multiplication, of course. If you have a times b and multiply them up, you can't get a and b back again. You have a little more information than that because of the basis, but you don't know the scaling factors. I don't have time for the details. So in the paper, the second half of the paper is about going from what I talked about so far, which is basically tensor algebra, to tensor calculus when things are varying in some space, in some manifold. So for example, then the basis will also have to vary based on position. So here is an illustration of a Cartesian basis. So this 2-dimensional space, it always looks the same, but if you have the polar system, then you have little base vectors which change by position. And the use of this in physics is usually using partial derivatives, and then you need a kind of derivative that would work with tensors, and it has this type here. So if you have any tensor, arrow from A to B, it will give a tensor with one more sort of argument, one more input, and you can see that's a directional derivative in that extra argument. And this is just for the teaser for the paper. This is what the general relativity curve space-time equation looks like. Remember that R was defined as 4 different terms using derivatives and Christoffel symbols, which in turns have an expression using a few terms using more derivatives and metric tensors. So everything is a big, complicated sum of derivatives of different sub-expressions, and everything boils down to how the sort of energy momentum tensor is translated to the curvature of space-time, which is the metric tensor G. So G is actually the variable you solve for. The tensor field G is what you want to compute from knowing a matter distribution in the universe. This was just showing the version, the diagram version of the curvature tensor. So in the paper, we don't solve this. I mean, it was solved by Schwarzschild in the same year as Einstein published the equations. But the sort of cute thing with it is that the solution has this strange behavior. So I could say just in 1 minute, it's a universe with spherical perfect symmetry and 1 point mass. So the simplest case, you want to solve something simple. You start with 1 point mass and then everything else is empty space. And then it turns out that you get this strange behavior like a black hole thing, that there is a radius inside of which nothing can escape. And why is that a black hole, just a 1 point mass? Because the point mass has infinite density. So regardless of how little mass you got there will be some little radius around it which will be where it behaves like a black hole. So there was sort of, in some sense, theoretical discovery of the black hole 100 years ago. This is what I said in the beginning, basically, contributions to domain-specific embedded languages. You can express these notations. If you do this particular expression, it means T is a vector field, U is a scalar field, and this expression is the directional derivative of U in the direction of T. So if T is the wind field over the Earth, U is the temperature, it's the rate of change of the temperature in the direction of the wind. In the paper, there's more stuff, and yeah, please, questions. I don't think it works. Maybe you can.
When it comes to the tensor product, did you consider, so there's a few ways you can think of maybe representing the language. One, which we see in things like iTensor in your work, is the kind of categorical approach to it. The other is maybe by the universal property. Have you considered like different ways it could be coded as axioms?
Well, I mean, as this is an abstract syntax tree of this in the background and so on. It's sort of it's axiomatic in some sense, you could say, and we don't really use any specific properties. I mean, it has to be a symmetric monoidal category for the transformations to work, but I don't think we represent tensor product in a specific way. I mean, the way we define it in the paper is by the universal property.
But in the language, you use just a symmetric monoidal category as axioms to
Yes. Yeah.
the universal property explicitly?
No.
Okay. Second question, are there tangent spaces?
Well, we don't have specific expressions for them, but I mean, they are there. Yeah. Yeah.
So like somehow, yes, right. But in some sense, like in the language, you do have a way to go from, like the non-index notation to the index notation. So like, what actually happens if I write down something that is in itself not non-tensorial, and I then say, please give me like, like the index-free version of it, and then I come back. Like, does it really? Yeah, like.
So we have a class for the partial derivative operations, which is sort of impure.
Okay.
It's not. It doesn't sort of satisfy the tensorial laws.
Sure. And then from that you build the covariant derivative.
Yeah, we implement the Christoffel symbols, and then we have to prove then that something is actually a tensor. I don't think the translation, because the translation isomorphism depends only on the underlying symmetric monoidal category representation. So that will, well, I guess maybe it just fails if it turns out not to be a tensor. I haven't tried.
Okay, yeah.
But it would be interesting to explore, yes.
Yeah, thank you.
Hi, thanks for the great talk. I was curious if you have any particular opinions or insights into what you are getting in your particular encoding from introducing covariance and contravariance, which is sort of, I would think of as the main, the upper and lower index, compared to the previous talk, and just think of, well, whatever, a tensor is an array of numbers. I know conceptually for physics it's very important, but do we have practical payoffs in introducing that into languages? Can we articulate what those are for people?
Well, I mean, this duality between inputs and outputs is what, I mean, as we use, how should I put it? I mean, one of the main motivations here was to be able to code up and give type errors for things which are not right according to the Einstein notations. So if you don't keep track of the upper and lower indices, you will be able to write sort of nonsensical expressions. In many cases, as there are lifting and lowering operators, you could sort of guess that, oh, they probably meant this, and then lower one or raise the other one. But then there would be this unclarity of what you actually meant. So we haven't implemented any sort of automatic inference of the index positions. I'm not sure if that answers the question.
I don't know. I mean it as a friendly question. I think it's an interesting, you know, it would be great if we have a really clear answer to that.
Well, I would say then usually in tensor computations, you don't change the basis. I mean, in the sense of TensorFlow, you just have this thing. And,
Sure.
and here you really want it to be base independent, so you should be able to change anywhere.
Yeah.
And then you really have to keep track of it.
So just wanted to make a remark to put a tie on the question I asked to the previous talk. So in that talk, tensors were always concrete, and only tensor operations were shape inferred. So if we wanted to make shape inference for tensors themselves, then it becomes helpful to distinguish the input and output components.
Yeah.
Thank you.
Okay. Now it should. Okay.
Can you check also the laptop here? Yeah, sure. Could you plug it? Oh, perfect.
Oh, now it, oh, it's on.
So did you switch it off?
That ooh, that is a. If it's green, it works, right?
Okay, so. Testing.
Then that should be fine. Can you try and talk?
Testing.
No, this is not fine. I'm sorry, yeah.
Testing.
Better, but yes. And I don't know if you want to put this in your pocket or wherever you feel.
I mean, I think you can put it on the outside. Exactly.
Yeah.
Have you connected your laptop already?
Not yet.
Yeah.
Okay.
Whether that's supposed to be something. Yeah, maybe it's just they set aside something. I think there's a lot of especially submissions this year. Yeah. Yeah. So they want all maybe this like the top 5 or something. Yeah. Do like we talk. Or you've got a cool looking machine. I like it. You're winning there.
I just extracted it out from the Google images itself. I don't know where it's coming from.
You should just animate it, have some lights going up and down, then it'll look really futuristic. Excellent.
Yeah.
Have you ever run the Haskell DSL on real hardware?
Yep, we did.
Really?
We did.
Exciting.
You're going to see a lot of like problems that we did. I mean, it's basically Qiskit and D-Wave, so pretty much we are converting from one Hamiltonian to the other and then like running it.
That is in the future. All right, just get water.
Okay.
Yeah.
Steal the stuff.
Yeah.
Okay, now it's unmuted.
Let's just wait 1 minute. Okay, I guess we should get started. Welcome to this first session after lunch. We'll have 3 talks in this session, and the first talk, Shandeepa will be giving about quantum.
Yep. Thank you. So I hope everyone's having a great afternoon, great day so far. I hope everyone's satisfied after their meals. So I'm Chandeepa. I'm from Iowa State University, and I'm a PhD student there. And I'll be presenting one of our works that we did on Haskell-based DSL for solving optimization problems, and we basically target quantum hardware. First things first, I would like to thank my collaborators, Dr. Lee, David, James, Dr. Amir first. Without them, this work would have never been a reality. Then I would like to thank the ICFP committee for accepting our work and letting us present in front of each and every single one of you. So quantum computing. This has been gaining a lot of traction since the last 3 to 4 years, right? You see news every day, like IBM has developed a machine that could host around 5,000 to 10,000 qubits. Google is coming up with something else. And then even D-Wave people, they come up with annealers. So there's a lot of traction or a lot of attention around quantum computing. So what actually can we do with quantum computing? based on the early progress, people started believing that they could somehow tackle NP-complete problems with this. This is not, so far, I mean, this hasn't been a reality. We do not know whether the speed up that we could get is real, but people have been trying. So quantum computing is coming. So we actually focused on one of the computational models inside quantum computing, the adiabatic quantum computation. We think this is a match, and a lot of people think this way. This is really a good match to solve optimization problems using the adiabatic quantum computation methods. I would call adiabatic quantum computation AQC to be short, and in our work, we treat the NP-complete problems as the optimization problem. So basically not the decision problem, but the optimization problem. So is this really new? No, people have been actually trying to do this. People are doing this. So what's really new, or why should you look at this work? This is one of the examples that you would get if you go to the D-Waves repository. This is, they are trying to solve a graph coloring problem. So yeah, you might see the word graph, but do you see whether it resembles the graph coloring problem? All you see is a matrix, like a set of weights, all of that. Maybe even specific stuff like chain strength. Is this what we really want to do when we solve optimization problems? No, right? This doesn't really make sense to us. So in our work, what we try to do is to retain the structure of the problem, retain the nuances in the problem, and then allow the programmer to write within that limits, and then compile into something quantum or something classical based on their needs. So adiabatic quantum computation, AQC for short. This is not your classical computer. This is not the computer that you would see in your day-to-day life. This is not even the unitary circuit model if you are familiar with a little bit of quantum computing. This is just another model of quantum computation which has been hiding under plain sight for a little while. Like a lot of people look at the unitary circuit model, but not this adiabatic quantum computation model. So what is the take here? In adiabatic quantum computation, we have something called the Hamiltonian. It is basically the same as the objective function you have in all of your optimization problems. The way you optimize this, the way you minimize this thing is quite different. It's not the same as you would do in your typical constraint satisfaction problem or any of your optimization problems. So what we do, we define an initial Hamiltonian, we define a final Hamiltonian, and then we try to slowly evolve the initial Hamiltonian to the final. The way we do this is actually a natural process. We try to basically simulate this in AQC sometimes. Sometimes we use real hardware to get this done. It totally depends. So the key takeaway here is that you have a Hamiltonian to be optimized, or to like capture your problem and then use that to solve your own problem. So we have the Hamiltonian. We have something called the Schrödinger equation. This is all physics stuff. We do not really think about this a lot. This is all background information for you. So usually what we do with when we solve for AQC is to simulate this, use the AQC approximation, and then use that to find the solution for your problem. So you have typical evolution there. You have matrix exponential terms. This H, the Hamiltonian, is a matrix, by the way. So we do that exponential, use this delta t terms for evolution, and then up until the time period t, and then we finally arrive with the solution. These are pretty much the background information that I would not dive into. Right. So we have an issue with AQC. What is it? we can of course solve problems with AQC, but the programmer himself will need to take care of the encodings, the hardware specific stuff, which he really doesn't have to do if their goal is to solve an optimization problems. So they will have to do these manual qubit manipulations, building different structures for different vendors, different devices. So that's not really our goal. That shouldn't be anyone's goal, to be honest, when they are solving these kinds of problems. So to solve this, we build a DSL, a functional DSL, for solving problems using AQC. Our DSL is basically built on top of monads and traversable type classes, and the takeaway here is that it permits a uniform programming paradigm for defining the problems in AQC. Now, as far as we know, this is the first high-level quantum programming language, and this allows the programmers to look at their programs as constraint solvers. Basically, we haven't been looking at those problems like this before, so this is basically the first time that we are thinking of quantum programs in this, at this level, this high level. So we basically built this DSL, and then we specify a bunch of NP-complete problems and some few other problems using our DSL. Then what do? We go on to solve these problems following a uniform compilation pipeline. It doesn't change depending on your backend, what hardware you are targeting on. And then we convert them to quantum circuits if you are using Qiskit. And then if you are using D-Wave, basically we translate it into a D-Wave program. Right, so the DSL itself is a Haskell library, and this allows the programmers to focus on their problems rather than the specific structures in their target hardware. So to get things clear, we have this pipeline. We have an input program. It is fed into NQ. We call our DSL or the entire pipeline NQ. We feed that program into NQ, and then we allow it to compile it to either a classical program or a quantum program. Classical program isn't our goal here, but we do really support that too. Right. When it comes to NQ, the single most important structure is this program or the data structure, program data structure. We have 4 parameters here: choice, struct, wave, constraint. But to know what these are, to define what these are, I would like to go through an example first. So we would basically go through the graph coloring problem. It's basically to say that we need to find a set of, a configuration for coloring the nodes of a given graph without having 2 adjacent nodes sharing the same color. So this is the program that we would write in NQ to solve the graph coloring problem. As you can see, we have defined all 4 parameters there. The first parameter is choices. We set the colors. We set all the colors that we use to color the nodes. That would be the parameter choices. And then we head on to specify these constraints. The constraints are basically all the constraints that we have for this problem. We define it using a mapping here. And the parameters there, the first parameter, basically we have a single list, and the first element is a tuple. So that tuple basically says a node accompanied by a color. And then there's another tuple, B, choice B, that is basically another node accompanied by the color. So in defining this constraint, we say if A and B define an edge, and if those two nodes share the same color, we assign a penalty of 1. Otherwise, the penalty is 0. So these scores basically aggregate up within the NQ when it compiles, and then it does its thing later on. But this is how we basically define the constraint. So why did I tell you about the constraint when we had the view here? So in constraint, we actually had two elements in the list that we provided. The view is the number of interacting nodes or the number of nodes that we use to evaluate in comparison inside the constraints when we define the list of constraints using our function. So since we evaluate pairs of nodes, we just set it to 2 here in graph coloring. So this is basically the explanation that I did for constraints, how we define it. A and B are basically nodes. Choice A is a color, choice B is a color. And then choice A is assigned to node A, choice B is assigned to node B. And then this is basically how we assign the penalty value for the violation of a constraint. Right. So we said that we also provide a uniform compilation pipeline, right? So this is basically the pipeline. We have two parts. We have a front end, we have the back end. In the front end, what we do is transform the program that we wrote into a certain form or a certain set of constraints and into a certain form that can be used by the back end to target different backends, like maybe D-Wave, maybe Qiskit. So we can even do classical simulation in the backend. So that's what happens in the backend. Right. So in the front end, we have 3 stages, and in the backend, we have just 1 stage. The first 3 stages in the front end is basically common for the classical computation and quantum computation, and the solve stage, since we target different hardware, it should be specific. Right. So let's say that we have 3 nodes in our graph coloring example in the graph. So let's label them by 1, 2, and 3. The first stage of the front end assigns a symbolic variable to each and every node in the list. So basically, it assigns var1x, var2y, and var3z. It's a really simple stage. This is all it does. In the second stage, we convert this list into what we call as viewpoints. So here we take the output of the first stage, convert it into the permutations of that list, but making sure that we only have elements with the length of the value in viv variable. So we said that in our example, we are only focusing on viv equals 2, that is to say we only focus on pairs of nodes. So we have only the permutations with length 2 here. Then we basically assign the choices, the values in the choices parameter, that is the colors of the problem, the colors that we feed into the problem, to each and every single element in the viewpoints list. So first we set black, we could say black, and then for that value, we single-handedly do all the other colors for the other variable. So this is what we end up when we finish the compilation with the front end, but we are not done yet. So the next stage is to solve this problem for real, like we need to get this into a hardware or get this somewhere or get this into a stage that we could use that to solve the problem. So classically what you would do is like brute force through the entire list, calculate the energy, and then minimize it. But this is not what we want to do. This is not our goal. So in compiling to quantum, we follow 2 stages. The first one would be to create this superposition state, and then the second stage, we need to calculate the energy or the cost function in a way that it supports the quantum Hamiltonian. So we convert the classical cost function to the quantum Hamiltonian. So when we build the superposition state, we take the output of the front end, the list that you saw, and then for each node, for each choice, basically for each vertex or the node of the graph, and for each color that you can assign, you assign a qubit. You have a single qubit for every pair of those. Then we set each and every qubit in superposition. We do this by typical Hadamard gates that you would see in quantum computing. I would not dive onto those. So Then what we need to do is to like encode this energy association, or like to convert the classical cost function to the Hamiltonian. For this, we basically go to the list of constraints, and for each and every constraint, for each and every qubit assigned, we assign a quantum operator called poly Z. In our implementation, we use poly Z gates. We basically assign those operators for each and every single pair of these. This operator should be capable of like penalizing the constraint when it is, penalizing when the constraint is violated, and basically depenalizing when the constraint is satisfied. So it should basically give a negative energy when the constraint is satisfied. So by summing up all these energy values or the operators, we come up with the problem Hamiltonian or the final Hamiltonian, and then we can build the AQC Hamiltonian with this. One thing that I should note here is that if you do pure AQC, like without NQ, you will have to build this initial Hamiltonian as well. So we have the final Hamiltonian, but if you are purely doing AQC, you will have to build this the initial Hamiltonian. But in NQ, we have a set of heuristics to define this initial Hamiltonian. So programmer only has to define this final Hamiltonian through the data structure that you saw. So this output Hamiltonian is basically very hardware independent, and it wants something continuous to like evolve this Hamiltonian into the final stage. But what we have in current hardwares or current vendors is the set of quantum gates. So it's a discrete process. So we need a Hamiltonian with a set of discrete gates. We do automatically do this compilation within NQ. We translate this AQC Hamiltonian into Hamiltonian with a sequence of quantum gates. So this is also taken care of by the NQ pipeline. Finally, we have a Hamiltonian which could run on real hardware. We have a set of gates. We have a Hamiltonian defined with a set of gates. But how do we get this to run on different hardware? We just have the Hamiltonian for now. So there should be a program, right? In order to run on Qiskit, in order to run in D-Wave, there should be a program. So this program we try to we generate within the pipeline after we get the final Hamiltonian. This is basically another simpler, smaller backend. So we did a bunch of case studies. We did equal sum, we did exact cover, we did type inferencing. Actually, we did 5 examples of case studies here. There are certain problems that could not run on D-Wave because D-Wave assumes the initial Hamiltonian by themselves. We can't really change their Hamiltonian in the way that we want. So certain problems cannot be solved with D-Wave. We did solve everything that we could. We tried NP complete problems as well as those in P. So for type inferencing example or the case study, this is the program that we wrote. We have 4 types. We have the integer type, and then we have a set of mappings, basically going from int to int, or mapping from 2 ints to ints, and then so on. So we define we define the constraint as here. So what we need to do is to determine the types of the expressions at 1, 2, 3, and 4. So we ran this example on D-Wave. We also did Qiskit. This is the output of Qiskit. So we ended up with having this solution. When you run on quantum hardware, you don't actually get the solution straight away. You do have to run it multiple times because there are stuff like noise correction, so errors happen. We need to run it for multiple times to get a valid solution. So this is what we ended up with. So the maximum frequency is for the first solution here, and then it resembles the types for each and every expression identified by this 1, 2, 3, and 4. So yeah, I think that's it for our presentation, our work. If you have any questions or concerns, I'm all ears for you. Yeah, that's pretty much it. Thank you. Thank you.
Any questions? Just use the mic though.
I can't hear properly.
Hi, thanks for the talk. I'm wondering if you have tried to compare the performance between the classic part of the program and the quantum stuff.
You always know the performance of the brute forcing, right? What we do is when we compare to when we compile to the classical backend, we try to do the brute force. So we basically have the brute force approach comparing against the other approaches like quantum stuff. But as per the paper, I mean, what we did in paper, we didn't go through a comparison between the classical and quantum backends.
A follow-up question is, but your problem domain is within NP and with optimization, then why don't you try to compare with some maxsat encoding of the same problem?
The thing is, like, you are basically asking whether we did a comparison between like classical backends and the quantum backends, right?
Oh yeah.
I mean, as far as the paper goes, we didn't do a comparison. Like, we didn't have to because we tried the brute force approach, and our goal was to like define this DSL to like compile into the quantum backend.
Okay.
Yeah.
Thank you.
So first, thank you for this very nice work. I'm familiar with this, but so do you have any metrics on like the complexity of the time complexity of the compilators and the space complexity of the result? Because ultimately what we want to achieve is in quantum computing is to get the exponential speed up. So, you know, if
I get your point, but our goal was to like define or redefine the way that programmers approach these things. We did not want to say that we have an advantage with this, but what we wanted to say is that we have a way for programmers to define the problems easily than what they currently do. So we actually do not compare between the performance, but we just provide them a way to define their problems easily.
But I mean, if, of course, like, but if using the DSL rather than directly coding end up having, you know, exponential time in the compilation, then...
Oh, no. Yeah, I mean, the translation itself doesn't really go, I mean, like, you can't, of course, like, go for very large problems, like, I mean, graph isomorphism, for example, you can't do that for like huge graphs, right? Even with the current stuff you have. But for every single problem that you have up there, like stuff that are like tractable using the current approaches, we can do using NQ.
Okay, yeah. Thank you.
Yep.
Okay, we can have one more question while Anil is setting up.
So I had 2 questions, but the first one was related, but it may be quick. It looked like, so for the, and please correct me if I'm wrong, but it looked like the assigned choices phase of compilation is potentially exponential in terms of the, so it's exponential to view in that it needs to select every...
Can you simply repeat the question? I didn't get
the
first
sorry.
part of it.
The assigned choices phase in compilation, because it has to list out all the combinations of qubits and options of size view, is it not exponential in view, or am I misunderstanding something?
I mean, if there are a huge number of choices, if there are a huge number of like constraints, it's going to be, of course, like a huge. I mean, by the number of input, I mean the size by the size of input, it's going to be exponential.
Yeah.
Once again, the goal here is not to look at the performance or anything like that, like not to look at the complexity. But what we try to do is to provide a way for the functional programmers, or basically the programmers, to define their problems in a way that is better than the current one.
Yeah.
Basically use the semantics in the problem to define their problem.
Yeah.
Properly.
And
Yeah.
is there enough time for a second question, or?
I think we need to move on.
All right, I'll catch
Thank
you
you.
later.
Thank you.
Thank you.
Okay, let's thank the speaker again. And for this next talk, we'll hear about that many people have had OCaml running on their laptops without knowing it for many, many years.
Thank you, Martin. It's quite cold in here. They told me that Singapore was a tropical country, so I'm going to try to warm us up by talking about something completely different now, which is reporting on about 10 years of work that we've done in an open source project called Docker. How many people here, just give me a show of hands, how many people here have used Docker in the past before? Okay, so most of you. So what I've been working on is a version of Docker that runs everywhere that makes it as easy to use as possible. So one of the key tenets of Docker that hopefully many of you will have seen was that our goal is to make the software process of building some software, distributing some software, and sharing it as easy and as friction-free as possible. So the basic idea is that I can just do Docker run of something, and then I can suddenly be in an environment where all of the software that the person who's publishing it intended to be shared is simply available. So in this case, I've got a playground for Oxidizer Camel, and then or Camel 414 in that case, and I can just use it. And I can find lots of other images from around the internet. There's about 14 billion of these published, which represent the file system images of lots and lots of other people's work. So the idea is to make it as simple as possible to pull that off. And then there's something called Docker for Desktop. And what Docker for Desktop does is that it tries to take this experience and turn it into a native application. So the idea here, if you look at my little desktop here, is that there's a Docker little whale, cute little whale sitting in my menu bar, and it provides all of the installation and sign-ins and all of the stuff you need to do. But really, what it's trying to make happen is make that command line available for people to use. So given how quickly the Docker project grew, the idea was to hide as much of the complexity of managing all these bits and pieces behind a single native application as possible, and just drag and drop it and have it just work. And we released this software in 2016, and there's been hundreds of millions of downloads since then, lots and lots of daily users, and Stack Overflow has generally voted it to be a very kind of developer-friendly project for many years in a row. But there was some drama along the way, which is what I'll tell you about, and how we fixed it using functional programming. So a very quick timeline for you is where it all began. It really has felt like a very short period of time, but it's been a decade already. Docker launched as a bit of a side project at PyCon in 2013. And it just solved this problem that was a pressing one at the time of how difficult it was to share Ruby and Python code among each other. And then when I joined the project in around 2014, there was a real panic station happening because most of the world's developers use Mac and Windows, certainly at that time, and probably more so today. But all of the software was being deployed in the cloud using Linux. And so the problem became, how do you take a Linux application and run it as easily as possible on the desktop, which is what people are actually using? And so while there had been a rapid growth in Docker for the first year, there was a real kind of barrier being formed to make it usable. And so then this is where I came in along with a whole bunch of people who I'll show you at the end again. And we started hacking on some systems infrastructure to make it easier and more invisible to translate between macOS and Windows and Linux. And then we released a beta of this Docker for Desktop, and that's the one that really started the growth and adoption, as anyone with a desktop computer could just start using Docker and deploying it as well. And then some OCaml code came in that I'll tell you about that fixed some critical problems, and the growth continued. And then over the next 7 or 8 years, there's lots of really good developments and adaptations. So we released a lot of the components as open source. Apple and Microsoft integrated sufficient pieces into Windows and macOS to make all of this just work seamlessly. And then happily, a majority of professional software developers report they're using this as a result of this work. And then excitingly for ICFP, we've also started integrating a lot of shiny new functional programming features into the code base to keep up with the times for needs for performance and so on. And so we're using effect handlers and direct style I/O, and I'll give you a bit of a preview about where we're going with that to show you what comes next as well. So this has been the overall timeline of where we came from. But first, let me explain to you what the basics of this application were and why we wanted to do it. The problem is that Linux containers are very Linux specific. There's a bunch of binaries that have been compiled, and they require a Linux kernel to run. You can't just swap a Mac kernel in there. And then our users are impatient. They simply want to run those binaries. And so we had to figure out, how do you build a native application that abstracted all of the gory details of running virtual machines, configuring the storage, making sure the networking works, and just make it so you just double click on this thing, and it spins it up. So our idea back then was, could we turn Linux itself into a function call? Can we just say, can we take the Linux kernel and do some stuff that will allow us to just treat it like any other library in our repertoire of libraries? So just like you link to libSSL, or you link to libmath, or anything else, could we do a libLinux? And then we built something called a library virtual machine monitor that made that possible. And so in the true functional programming style, our goal is to make Linux an implementation detail of the application. And the benefits are the users just have a simple application experience without all the gory details to worry about. Does that make sense? OK. Now, this would normally be really hard. Like, Linux really does not want to be squeezed into a library structure. Linux is used to running in a complete environment where it runs all of the hardware. But luckily, another technology came along about 20 years ago called Zen. And Zen began this support for virtualization. And the idea behind virtualization is that you can fake out an environment where Linux can run, where it believes it's in control, but it's really running through software, device drivers, and equivalents. Now, the problem with Zen is that you can't run that on desktops, because Zen also needs to take over the entire computer, whereas we need to run as an application. But luckily, what happened was that in the intervening years since Zen, in about 2003, Apple and Intel and AMD and Microsoft added just enough support into the hardware and the kernels that we could have these little hooks to use hypervisor functionality from user space. But no one really knew that this existed. So we kind of did some rooting around and looked at some undocumented APIs and discovered that there was actually in green lots and lots of hooks available that if we used, instead of using them to run hypervisors, we could use them to run inside desktops. And then from there, the rest would be easy. We could build libraries to use them from user space. And then we could do the work in Linux, and we could run the whole thing as an application. So this is the 2016 plan. There's been lots and lots of different pieces, but it was all fragmented, and nothing really quite worked together. So here's how we kind of made it work, just to give you a sense of the architecture of this application. And then I'll talk about the functional programming pieces. So our goal is that we want to say run Docker run, just like I did here. I want to Docker run Debian. And I want it to run some command and have it actually do something useful. So the idea is that when I do a Docker run, it should download all of the images of Debian. And it normally does this inside Linux by running inside user space. There's something called a container runtime interface, which sets up the file system. And then it allows you to access the network. And then Linux does its job. It connects to what you want to find, and it returns what you requested. In this case, it's requesting the camel.org website. So this works great if you're in Linux. But then we want this to work when our client is on a Mac, yet it somehow has to find a Linux and go through and give us the result that we're looking for. So the way this works is we can build an application that links a hypervisor as a library to kind of pull this off. So we're just going to add a few more layers in between to see if we can just make this work without anyone noticing we've done all this stuff. So the first thing we do is whenever we launch our Docker for Mac application up here, we spin up this hypervisor framework. And the only thing this hypervisor framework does is that it hooks up the right hardware instructions so that you can actually run a virtual CPU or a set of virtual CPUs inside user space. So it takes care of creating the fake kind of virtual CPU environment. But it doesn't have anything else. It doesn't have an operating system or anything else. It just lets you run a function call. So that looks a little bit like this. It gives you some low-level C code where the interface that you have is that you can call into C function calls when they would otherwise become hardware operations. So if I need to spin up a virtual CPU or have an interrupt or the things that you would normally write low-level code for, they just become single-threaded callbacks into your application. So it's like a C function, right? And so in this case, we're just initializing a virtual CPU. And as you can see here, it's just creating lots of fake things for interrupt controllers and PICs and all of that kind of stuff. And then ultimately what it's doing is that it's just calling some functions. And we know how to deal with functions, right? They're just like any other library. And then from there on, you want to say, well, how do I want to program the rest of my operating system? So one path is write a lot of C code. And the other path is write it in a high-level language, because there's lots of policies that we want to deal with. So we want to figure out how to manage our storage and expose configurations to the application. We want to build a nice user experience. So the next thing we did was link in the OCaml runtime. So at this point, we have some low-level C code, and then we're trying to boot up a version of Linux. So we're like, OK, let's manage Linux from OCaml. And so at this point, just the standard OCaml FFI is linked into the application. And if you're familiar with the OCaml FFI, it allows us to just deal with low-level OCaml bindings, in this case for a block device, so we can have storage. And there's no real modifications. This is a standard OCaml FFI. But crucially, what this set of bindings does, it lets us shift our level of abstraction over into OCaml from the low-level code. And at this point, the first thing a Linux is going to need when it runs in your application is storage. And storage is notoriously difficult to handle, because you have file systems, you have to break things up, and users want to delete different things. They complain when they delete them, and then you have to recover them. So you need a lot of policy to manage it for this many users. So we wrote a custom file system in OCaml called QCOW, which is a storage format that is often used by virtual machines. But because of these bindings we did, we could take the low-level C calls from the low-level hypervisor and essentially build a file system that is much more expressive and high-level. So in this case, in the case of block requests, you're dealing with offsets to various parts of a sequential device with fixed size buffers. And our OCaml code that has been bound to the low-level HyperKit code looks like a request structure where, if you're familiar with OCaml syntax, we have an ADT here. We have nice high-level configurations. C structs represent blocks of memory. And then responses also look the same as well. And we have nice little error handling and so on, where we can pattern match and do all of those nice, good things. So at this point, we're now getting to our goal of running Linux. We have a low-level hook into our operating system. We've written bindings to manage the storage in OCaml, so we've got high-level code. We then do some gory details to manage shared memory, which gives us something to write into so that we can then communicate with Linux. And before you know it, we have an aperture where we've booted Linux successfully now inside the application. And in order to pull this off, you don't want to be booting up desktop Linux. So we wrote a custom Linux distribution that is fully immutable and boots up in just a few seconds. It's called Linux Kit, and it's still maintained. Last commit was 2 weeks ago. And imagine it's the minimum Linux you need to run Docker. So everything runs inside a container. It boots inside about half a second. And it does nothing. Its sole purpose for existence is to just set up everything you need to run the kernel. So there's lots of these kind of immutable Linuxes now, but Linux was kind of the first as well. And from there, life is good, right? In theory, you should be able to simply move forward and then bridge traffic to the outside world. And you do this by taking all the traffic that comes from Linux and just copying it and sending it over your host network, and everything should be fine, right? But then we got maybe, we released this, and we got maybe 10,000 bug reports in the first hour. There was a lot of users on GitHub, and my GitHub notifications haven't really recovered since. The problem was that every corporate user discovered that it looked like a bit like a virus, because from their perspective, it looks like there's a new computer that is transmitting traffic that isn't your desktop. And so we really had to figure out how to fake it out so that it looked like your Mac was sending the traffic, or your Windows was sending the traffic, not this weirdly hidden Linux library thing out there. And so the answer came from the 1990s. How many people here have used a Palm Pilot here? OK, there we go. Yeah, Simon's old enough in the back, but he didn't have one, I guess. But what these Palm Pilots did was, it was a way to manage your life in the 1990s, and you had to synchronize it with the computer. So it had a little protocol that would reconstruct the low-level network traffic from the Palm Pilot and turn it into high-level socket calls that you could then invoke from the other side, from an IRDA connection, an infrared connection back then. But the basic idea is that we want to take the low-level Ethernet frames and then convert into the high-level calls, and then use those high-level calls in order to replay the traffic in the MAC, so we've totally faked out exactly how this system looks to the outside world. We have no more hint of Linux at all. It just looks like the MAC is sending the traffic. The question is, how do we reconstruct this network traffic? You've got to start from low level. You need a full network stack, right? From low level Ethernet traffic. Then you've got to build up your views of TCP flows. Then you've got to have HTTP flows, then TLS. There's a lot going on here. So luckily, in our repertoire of tools, we had something called Mirage OS, which was a full operating system written in OCaml for various reasons. It was fun. But what it did was we had all of the libraries in OCaml, and we'd already bound OCaml's runtime into our application. So what we did was we reversed the network stack by writing a bunch of code. And the reverse network stack looked at low-level traffic. It pattern matched on it. It constructed high-level data structures saying this is an HTTP request to this other endpoint. And then it translated that into macOS calls. And overnight, the bug reports dropped, celebrations were had, and the growth of Docker continued unabated. So what this Rube Goldberg's machine kind of looks like is that we've started off by spinning up a hypervisor. We've written some orange OCaml code for the storage. We then have a custom Linux distribution for the file system. And then we have a bunch of OCaml code to translate the outputs as well into something that the Mac can then use to look like it's just a native Mac app. So we've now successfully turned Linux into a function where everything from here to here is fairly high-level code. And then while there's a lot going on that's virtualized in Linux, it's no longer exposed. And there was quite a lot of OCaml code to make this happen. And I'm just going to spend a few minutes describing some of the good bits, the crazy bits, and the ugly bits, just to give you a sense of what our experiences were like using OCaml during this time. So the first thing is that because our networking code is so modular, because it's written in OCaml, we heavily used signatures and functions to kind of pull that off. So for example, here, we have OCaml signatures where we can include different combinators and signatures in order to assemble the structural interface we want for this, for example, for the output from the Mac or from Linux itself. And then we have maybe over 100 module types that represent small pieces of network stacks, and you can assemble them together. And then we can use OCaml's functors, which are parameterized modules, in order to choose which levels of implementations we want to assemble to match those structural signatures. So in this case, for example, we can bind into a socket, for example. We choose we want to forward from the Mac, or we want to forward into the shared memory channels. And we could reuse a whole bunch of the signature implementations to make sure that we'd match the networking that was coming in to the networking that was going out. And then ultimately, the entire stack looks like a bunch of applications of functions. So I'll give you a very swift preview here where you can see OCaml code inside VPNKit, where we've got lots of higher order functors here making things. You've got lots and lots of applications of them in different formats. And then if I scroll all the way down, you've got lots and lots of pattern matches and stuff to intercept different parts of HTTP and kind of pull it off. But it's complicated, but it's a lot less crazy when you're doing it in high-level languages, because we can reason about things in a nice typeful way and use the OCaml module system to assemble the complexity into manageable chunks where we can test them independently as well. So generally speaking, the core OCaml features were remarkably useful here. So we often forget just how good it is to do ADTs and pattern matching and so on. And then just having a stable and predictable foreign function interface that hasn't really changed that much under our feet for over 10 years was actually really useful, because we were in one process. We were managing lots and lots of runtimes linked together in the same address space. So Swift, Go, OCaml, Objective-C, and I'm sure some other languages snuck in there as well. And it kind of made the whole thing a lot more attainable. But performance did start to drop a few years ago, and things were getting a little bit slower. And the problem is that we used a lot of monadic concurrency in user space in order to pull off all of the proxying. So this is classical OCaml, where we didn't really have any way of baking scheduling into OCaml. And so a lot of the code involved expressing that through some kind of higher level library. In our case, it's called LWT. More recently, we released OCaml 5, which has effect handlers. And that let us rewrite a whole bunch of complicated networking code to look much, much better. So just qualitatively here, the right-hand side is the direct style OCaml code, and the left-hand side is the code using LWT. You can see here on the right-hand side, we no longer have monadic binds. We simply use direct style copying. We no longer need to parameterize our inputs and outputs as functors. We no longer need to have error handling at the monadic level because we just use normal OCaml exceptions. And the code has become just smaller, tighter, and simpler for that reason. So direct style EIO programming has been quite a successful use of taking something that did work before, but was very allocation heavy, and then turning that into something that is much quicker and more manageable. So that's the direction we're going in now. So overall, to summarize, OCaml's been a very solid choice for putting together a system that would otherwise have fallen apart under its own weight. Because there's just so many moving parts that it gives a clean abstraction boundary to manage the operating system side of an application while keeping it invisible from the user as well. Once put into production, it's been rock solid. There's been bug reports, but nothing that made us panic like those early days of 2016. So we've had hundreds of millions of users run this on all kinds of desktop machines as well. And this trick of using the kernel as a library is now emerging and is applicable to lots of other different systems. So WASL, for example, is WebAssembly running on Linux. I was just chatting to Ben yesterday about how we could pull this off. And so there's lots and lots of use cases for taking this architecture and applying it to other places where you might need to translate a Linux kernel into something that you want to manipulate from your programmatic user space. And of course, performance is good now, but it could be better. And so we ran a tutorial in Oxidized Camel where you've got Rust-style region management and so on. So that's another exciting direction where we're still trying to figure out, the language aspects, but it looks like we should be able to get this to really good wire speed performance soon as well. So I'd just like to conclude by thanking many, many contributors to this project. We've had hundreds and hundreds of people contribute to VPN Kit. Some of them are named here. And generally speaking, my deep gratitude to the OCaml and MirageOS developer teams for helping us with lots of bug reports and assistance over the years as well. It's made the project possible, and we've really enjoyed working with them as well. Thank you very much. Whew. Oh.
And we have time for a few questions. Just line up.
Thank you.
The storage layer, was Ermin involved at all?
Ermin was involved. So Ermin is a Git-like management store for a while. We actually use Ermin for the coordination of the app through something called DataKit. So DataKit is now archived, but it's a Git-style coordination layer that would let you write things into a virtual file system, and then it would apps would use that as their logging layer. So it was never in the data path, but it was in the control flow path.
Thank you.
Thank you for the talk. I guess one thing I know about OCaml is that its Windows support has often been lacking, but here it seems to be that maybe even despite this, using OCaml helped the whole cross-platform thing actually be possible. I guess any comments on how that worked out, or if there are any things?
It's good. So OCaml's always had really good Windows support as a core compiler. So my colleague David Alsop works on this, and we had pretty much zero bug reports on the Windows side. Where OCaml is perhaps been lacking is the ecosystem of libraries, because that's harder. But in this case, we just build a monorepo. Everything compiles on Windows using the Dune build system, and there's almost no bugs. We have bindings to IOCP and things, which just take care of things.
That's great to hear. Thank you.
The story about enterprise software is a fun one. Reminds me of when TLS 1.3 came out and everyone freaked out and all the boxes were blocking the traffic. So have you seen security software mellowing out since and being more like chilled about seeing bridge networking interfaces all over their internal networks, or is it still a huge problem?
No, it's still a huge problem.
Still?
100% a huge problem. So there's more and more proxies inside networks now. So VPN Kit is expanded to support protocol level authentication. So you can authenticate to a corporate proxy with with SOCs and so on in order to pull that off. So now it's more of a cooperative thing with the security proxies, but it still needs to reconstruct things in order to know what's going to be sent as well. So it's security is definitely not chilling out, but it's getting more manageable, I think.
Okay, good. Thank you.
Thanks, Joe.
Okay, and while we're just setting up, let me just ask a final question here. So, OCaml, where do you think it will have the biggest effect? Where do you see the biggest memory issues with the?
We do a lot of dynamic lifetime management at the moment. And so just having the ability to control regions and then make sure that we can do local stack allocation and do race-free parallelism. So all of VPN-Kit is single-threaded right now. And so having a way to do structured multi-core parallelism and hardware offload would give us the next level of performance as well. So we'll get there. It might take a few years, but it'll happen.
Okay, let's thank Anil again.
Thank you.
And for the final talk here, we will hear about knitting, and Nath is going to give the talk.
Thanks for the introduction. So works so well with Docker. So raise your hand if you've used a knitting machine before. Oh, wow, a couple more people than I thought, but the good news is that many of you are wearing a knitted object on your feet, probably socks. So we're all machine knitting users by heart. So this talk is about machine knitting, which isn't really a common ICFP discussion. But on screen right here is this diagram of the knitting machine. And it's this fully automatic mechanical marvel, and it's roughly the size and weight of a fridge lying on its side. It's super expensive too. They can be used to create garments of all shapes and sizes. And then if you take away one thing from this talk, I want it to be that machine knitting is this exciting and interesting form of non-traditional computing. And as PL researchers, we're used to improving computing using our research, so why not try machine knitting out? So to start out, I'll just have the basics of machine knitting. Every knit object is made up of these things called stitches. Every stitch is when I take a loop and I pull yarn through it to form a new one. So right here we've got 5 stitches out. With hundreds or thousands of these stitches, we can tile them together to form these functional and fashionable knitted structures. Knitting machines can manipulate yarns to do all this automatically with absolutely no help from humans required. And then they have hundreds of these hooks that will hold, pull, and transfer yarns to get the desired result that a programmer wants. So machine knitting is used to make almost all those knitted objects that you find in stores, including but not limited to socks, sweaters, gloves, and headwear. And then high-end knitting machines, the ones that we're studying in this talk, are quite powerful. They can make these beautiful patterns and textures and colors. And then they can also be used by researchers to make, for example, the graphics people have the Stanford Bunny. And then the soft robotics community has been able to use machine knitting to create some really cool tools there. So many machine knitting programs are written in these low-level languages that require the user to manually specify which actions the machine should take. And they're quite similar to assembly in traditional computing, but these languages are specifically straight-line execution. So there's no recursion, loops, or jumps. So these instructions are these atomic machine operations. For example, here's one operation that's performing a single stitch with one of those hooks. So it pulls the loop through the loop, and it creates the new one. Because these languages are so fine-grained, they're not easy to use. So programs can have thousands of these stitches, and managing this whole machine state can be very challenging on the programmer. I want to draw this analogy between machine knitting and traditional computing. So traditional computer operations are moving bits between registers, and machine knitting moves yarns between the hooks. So basically, the yarns are sort of the values of machine knitting. Traditional computing is often studied where the only observable behavior is the final state of the machine, what the result of the computation is. But in machine knitting, the observable behavior is this physical program trace. As the yarns move throughout the machine, they leave behind this literal physical 3D trace of the yarn. And so when you get the object out, that's really just a program trace. So this is my exciting takeaway. Your socks are physical program traces. So now back to programming these knitting machines. Researchers have developed these higher level languages and tools that can abstract away some of the details of the machines. And these high level languages will then compile down to those low level machine operations. They're generally much easier to work with. But there's this problem. Low level languages lack these usable, rigorously defined semantics. So as a design is compiled into those low level operations, there's no notion of program meaning to consult.
And then because these equivalences aren't well understood, the compilers are quite conservative in their optimizations that they can make. Additionally, they can contain bugs, and then the high-level design tools often purposefully limit the expressivity of the garments they can create just because of the difficulty of effective program analysis to compile down to operations correctly. And then this is the problem we're addressing in this talk. We need to have semantics. This hopefully shouldn't be an unpopular opinion at ICFP. So prior work has developed a definition for machine knitting semantics, but those semantics are purely topological. So the programs would denote these tangles of yarn that are embedded in 3D space. Two programs are equivalent whenever their tangles can continuously deform into one another, just like in knot theory. So topological equivalence does allow all sorts of stretching and deformations of yarns, but in the real world, there are some physical limits to how much yarn can stretch before it breaks. The two knitted objects actually have to have similar yarn lengths as well as the same topologies in order to look and feel the same. So this prior work and our work by proxy don't consider the yarn lengths, so that's a slight limitation, but we do believe that those yarn lengths could be added in. We're just focused on the topology for now. So an important technicality is these authors' uses of these dashed lines right here. They exist to topologically separate the stitches from the other parts of the work. So they prevent the yarn inside the dashed lines from escaping and interacting outside. So you can think of it as if I've nailed down the yarns at each of those points along the dashed lines. So because these semantics are relying on continuous deformations, they can sort of be unwieldy. The authors only described a limited set of program rewrites in their paper, but in our semantics, we're able to fully characterize program equality. Now, we're deciding machine knitting program equivalence in polynomial time, which should be an alarm bell. Most languages don't have easy program equivalence, but remember our language is straight line, so we have some hope. Knot theorists haven't been able to find an algorithm for polynomial time knot equivalence, despite working very hard on the problem, so many of them suspect that an algorithm doesn't exist. So instead of solving a long open problem in mathematics, we've noted that only certain types of topologies can be output by these knitting machines. And so we're providing a polynomial time equivalence procedure only for those knots that the knitting machines can make. So we're encoding our topology using category theory. So to summarize, machine knitting is a pretty important fabrication technique, and there are a lot of connections to programming languages, but there aren't computable semantics yet. So now I want to discuss how we've approached this problem. So our work has adapted those previous topological semantics, and we're instead using string diagrams to discretely characterize the knitting topology and almost all of its equivalences. And I see some laughs there. Yes, the string diagrams are actually string diagrams now. So due to some quirks in how yarns begin in the knitting machine, our semantics don't capture a limited class of equivalences at the very beginning of some programs. We do have some future plans to adapt our semantics to recognize these equivalences, but the vast majority of the equivalences are captured by our models. So our diagrams represent the topology of yarn in 3D space. So whenever two yarns cross, one goes above and in front of the other, and that matters. So these two diagrams on the left are different. For those of you who are familiar, it's a braided monoidal category. And then our diagrams are actually graphical representations of a morphism in a category that we define in our paper. We'll use the diagrams wherever possible in our presentation, but fear not, category theorists, there's plenty of notation in our paper. Now, our semantics don't represent all knots. Knitting machines don't allow yarns to turn around and change direction outside of the stitches. So this restriction is what's allowing our program equivalence to run in polynomial time as opposed to general knot equivalence. So our semantics are suitable to serve as an intermediate representation for machine knitting. So a high-level design tool could target our semantics, and then a single compiler could translate to these optimized and correct low-level machine instructions. We also have some hope that our semantics might enable functional and formal high-level machine knitting tools. Our second contribution is a canonical form for our categorical semantics that we can compute in polynomial time with respect to the program length. This was surprising given the difficulty of knot equivalence. So this gives us polynomial time program equivalence because just given two programs, we calculate their semantics, calculate their canonicalization, and compare directly. Because our semantics are representing the topology of knitted objects, our canonicalization can be interpreted as this deformation of yarns in 3D space. So our equivalence algorithm has some immediate applications in translation validation, but the theory that we developed has some broader applications in the formal study for machine knitting. And this is the key contribution of our work. We are canonicalizing programs in polynomial time by deforming their output objects in 3D space. So our semantics are based off of this correspondence between certain monoidal categories and the topologies of string diagrams. So category theorists have formally proved that the topologies of these graphical diagrams are faithfully representing the monoidal categories that they're meant to. And we're using their result in reverse. We are instead representing our topology with category theory. So we represent machine knitted objects with the axioms of something called twisted involutive monoidal categories. These add some more 3D structure to braided monoidal categories. The objects of our monoidal category are these lists of yarns where the list forms the monoidal structure. The identity morphism just keeps the yarn straight and unchanged. Stitches are represented by morphisms as they map one list of yarns to the other. And it's not critical for our presentation here, but our diagrams are read bottom to top because that's actually how knitting machines create the objects. We draw the monoidal product as a horizontal concatenation. So given any two diagrams that represent morphisms, their monoidal product is just those two diagrams next to each other. They're being knit in parallel. And then there's this braiding isomorphism that crosses one yarn over another, and then its inverse is just the opposite crossing. And then here it is in the context of a monoidal product. And then finally, we can draw a categorical composition as vertical concatenation. So given any two diagrams whose yarn objects agree at the boundary, we can just compose them by pasting them together vertically. We're knitting them in sequence now. So the big takeaway of all this is that each of our string diagrams are actually morphisms in a monoidal category. And every portion of our diagram is a morphism of our category, and these morphisms will tile to form the knitted objects. Now, in most diagrammatic contexts, equivalences like De Morgan's law right here can change a diagram's connectivity. So here, 3 gates are equivalent to 2 gates. But those prior semantics for machine knitting stated that those internal yarns cannot interact with the outside because of those dashed lines. So for the purposes of equivalence checking, we can temporarily just ignore those internals and draw all of our stitches just as these boxes. Categorically speaking, the algebraic structures representing these stitches are free. There is no way to rewrite compositions of stitches. It just is what it is. This is a key insight because now we've reduced our equivalence problem from the topologies of yarns to these comparatively simple string diagrams. Because of this, any equivalences between the diagrams come only from those axioms of twisted involutive monoidal categories. We formulated these 7 complete rewrite rules from those axioms, so diagrams are equivalent if and only if there exists some rewrite sequence between them. And then all of these rules have a physical interpretation, shown here. By setting up these semantics, we've reduced our problem of program equivalence to deciding whether there's a sequence of 7 rewrites between the diagrams. So to cap up so far, we've taken program equivalence to topological deformations, to category theory, and now into these 7 rewrite rules. And on our paper, we're defining this procedure that will canonicalize the diagrams up to those 7 rewrite rules. And I'd like to dive in on this technical point in our canonicalization algorithm. So our algorithm works in 3 stages, which use our rewrites in different ways. Our first stage is called layer. It pushes the complexity of yarn crossings down the diagram as much as possible. It operates as a top-down sweep. It simplifies the top of the diagram and keeps on pushing down and down and down before simplifying the bottom. After layer, we use swap to vertically reorder stitches to achieve a canonical order of them. So in this example, we just swap those stitches places. And then finally, we use braid to simplify any remaining yarn crossings. The most difficult part of our algorithm is the swap step, because we somehow need to decide whether two adjacent stitches are able to swap places vertically. So this swap detection problem is really difficult because the diagrams are in 3D. On the left here, the stitches A and B can swap. A's red yarns both pass under B's, so they can just slide right past each other. But on the right, C and D are locked together. Due to those yarn crossings, those stitches are snagged on each other. And now I didn't run out of animation budget here. I just wanted to show this is a real world problem. This snagging problem is not an arcane categorical or topological construct. It is very much the same idea pictured here. The cables just are snagged. I cannot pull them apart. I cannot push them apart. So unfortunately, the snagging problem can be quite intricate. In this example, these two stitches appeared maybe to be snagged, but we later show that they can swap. And then here's where our categorical representation will come in and save the day. We can use category theoretic techniques to provably detect snagging. So we'll use this simple example to demonstrate our snag test. We're interested in this middle chunk of yarns called X, and then whether it contains any crossings that will end up making A and B not be able to cross places. So objects like X are quite well studied. X is called a braid within the braid group, whose presentation is on screen. In fact, these three rewrite rules of our diagrams are exactly the braid group's presentation. And we'd like to separate X algebraically into two braids, which we'll call X sub B and X prime. The X sub B part should represent the portion of X that the B stitch can topologically slide past. And the X prime part would be the portion of X that it can't. That is, X prime is snagged with respect to B. I can't get rid of it yet. To achieve this decomposition, we can use a pair of adjoint functors. So our first functor rho will project out certain yarns in X. See our paper for the details. Here, rho is projecting out 2 yarns, leaving a strand on 4 yarns. And then we use a second functor phi to restore those yarns that rho projected out, constructing X sub B, the portion of X that can slide past the B stitch. After finding X sub B, we can just calculate X prime by subtracting out. And as we noted earlier, there's this adjoint relationship, and we in fact proved that they're a reflection, which means that repeated projections and reconstructions have absolutely no effect. The key idea here is that our braid functor composition keeps the X sub B part and destroys the X prime part. So after decomposing X, we can just slide the B stitch up past the X B, leaving only X prime between the stitches. And then because B can't slide past anything at X prime, A and B can only swap if A can slide all the way down past X prime. In our example, we've chosen X to have this straightforward graphical decomposition into X sub B and X prime, but it's certainly not common in general to have that. Now we're just going to repeat our trick, but for A, we're going to separate X prime into 2 braids, and then after sliding, we're left with X snag between A and B. By the previous steps, we can be certain that both A and B cannot move past X snag. So because X snag is not the identity braid in our case, we can safely conclude that A and B cannot swap places. And then in the converse case, A and B can swap places. Now, I said earlier that I'd show that this example is not snagged. Our first step will move roughly half of the yarn crossings below the bottom stitch, moving B all the way up past. But now there's really no clear relation between those because there wasn't a clear graphical decomposition. Our functors are doing all the heavy lifting here. Then our second step will just move the remaining crossings above the top stitch, showing that the 2 can in fact swap. But this isn't particularly satisfying, and I would forgive you if you don't trust me here. So I have one more animation to show you. So here's the decomposition of X into X sub B and X sub A that our functors calculated. There's this clear correspondence between X sub B and the braid that ended up below B, and then the similar for X sub A and the braid that ended up above A. And for our decomposition to be correct, we need some sort of rewrite sequence between our original braid X and those decomposed braids X sub B and X sub A. And then here's the animation of that. We're rewriting X into its decomposition. And this is sort of the key idea behind our snag check. We are using functors to cut through all of this noise of the algebra right here. We are untangling the braid into its pieces. The decomposition and the animation are just for the presentation's purposes. In the implementation of our algorithm, there's no requirement to compute all these braid rewrites. We just shove it all through the functors and run with it. So that marks the end of the category theory, and now I can wrap up this talk with 2 more slides about our main results. So in our paper, we've proved that our canonical form is computable in polynomial time. And this is super exciting because efficiently computable canonical forms are very powerful, and we also learned a little bit about what makes not equivalence difficult. Now, I should note that the worst case bound that we provide in our paper does not look friendly at all. Its highest degree is m to the 7th, where m is how many stitches there are in a program. Now, this is because our proof doesn't rule out the possibility that diagrams become larger every time we perform a step of our rewrites. We haven't noticed any such behavior in our limited testing so far, and we do have some suspicions that some clever mathematics might be able to alleviate those concerns. We also estimate that on typical machine knitting programs, the runtime will be quadratic in the number of stitches in the program. Nonetheless, we're extremely happy with our polynomial time result, and we've left more careful algorithmic analysis to future work. And then we've also formalized our canonicalization algorithm as an abstract rewriting system. We proved that it's sound and complete up to our 7 diagrammatic rewrites. It always terminates, and that it's confluent. With both termination and confluence, we have that the ARS is canonicalizing. And then because it respects our diagram rewrites and they're equivalent to those categorical axioms, we have a canonicalization of our semantics. That's all I have to share, and I'm very interested to hear your thoughts and questions.
Hello? Oh, great. Okay. Early on, you mentioned that you're interested in partly to do optimization. And I assume to do optimization, you take the high-level program, and then you have a class of sort of low-level traces you can construct, and they're sort of all equivalent in one sense, but there's some other sense in which they differ, like, and you want to pick the one that's best in some sense.
Yes. So I've got a great answer for that. So turns out these knitting machines are basically a vector-based architecture.
Yeah.
So they have hundreds of these needles, and they can all operate in parallel. So the way to make a program faster is to do as many stitches as you can at once. So we try to...
You're optimizing for speed?
Yes,
Okay.
optimizing for speed. There's also another couple metrics that we can optimize for, such as reliability and then geometric relation to the original, but we're mostly interested in speed right now.
Thanks.
So the main contribution of your work, I haven't actually read your paper, is of this abstract rewrite system. What, if any, role does it play in the word problem for group presentations? Is there some is there something that can be reused there, and do you use any existing algorithms for word presentations for braid groups?
I mentioned the braid group earlier in this presentation, and then right here we have this step called braid, and that is exactly using the word problem for the braid group. So we're already using some of the group theory here, but here we're using category theory because these objects now don't have complete composition. So in terms of the word problem for groups, we're in a different setting, but we are in this sense solving maybe the word problem for twisted and volutive monoidal categories of a certain knitted structure. So there could be some applications, but we haven't formally looked into that yet.
Okay, maybe one more question. So it seems like the black boxes here, they don't know anything about the colors of what is coming in and out. So I guess that, would it be possible also to do some conditional knitting where you basically have some constraints that maybe if there's the same color you can do something, otherwise do something else? Or would that require some staging? Or?
So knitting machines don't have any way to take input or read like what their values of their colors are, so they just perform the same operations. So you could maybe perform some sort of actual traditional programming language, and then that operates based off of what's being knit and combine them. But currently we wouldn't be considering those equivalences. We're just considering with these static straight line programs for now.
All right. Well, let's thank Nathan again. I believe that somehow concludes the session, but there seems to be some other things going on. Yes, is that in this room? Okay, so who is chairing that thing? I was not instructed at anything about that, so maybe someone knows. Yes.
Okay, yes.
That will be you.
Yes, hi, sorry. We have 6 SRC finalists, and so we will have the pleasure of hearing lightning talks from each of them. These talks will be 3 to 5 minutes. Each slot is going to be 5 minutes. So we'll probably have time for 1 or maybe 2 questions. And as people are asking questions, we'll have the next SRC participant come and set up so we can start on time. And if you give us a moment to establish an order very quickly, we'll get right to it.
Yes.
Hello, yeah. Nice to meet you. Yeah. So. It's hard.
Do you want a time warning?
Sure. Yeah. 5 minutes, right?
Five, like the high end.
Yeah. Could I have a warning at 30 seconds, or is that
30 seconds from 5 minutes?
Yeah. Sure,
we can do that.
Okay. And how do I stream to the like HDMI? Yeah.
Yes.
Sorry. Yeah. Give me a sec.
Okay.
Yeah.
Display.
This is. Windows.
Yeah.
Yeah. Multiple displays.
Yes.
That's not working. Advanced display.
Can only
you
see
plug it?
Yeah, I'm gonna try again.
And maybe you get
oldest solution in computer science.
Sorry.
Oldest solution in computer science.
select the display. Yeah.
There's only one display.
You don't see it?
Yeah, I don't see it.
Weird.
It should work, right? Just now it worked.
Yeah.
Yeah.
Maybe we can go on with the next person, and I can give you my laptop if you want.
Okay, sure. There's a problem, so we'll go for second and use. Yeah. All right.
If you want to share your slides with me, I can.
Sure.
Can you
Yeah.
give me your?
All right.
Yes.
Did I just start?
Our first lightning talk. Our first lightning talk will be from Yang Tzi.
Go ahead. Oh, all right. Thank you, and welcome to my talk. I'm Yong Tzi from the National University of Singapore. My advisor is Prof. Michael Adams. Yesterday, you might have heard my talk on trees. Today, I'll be talking about something different, which are graphs and static analysis and parsing, type checking, automata minimization. What do these problems all have in common, right? Well, these problems all involve self-reference and cycles. And the computational essence to these solutions to such problems are what is known as a work queue algorithm. Work queue algorithms maintain a work queue and repeatedly does some work to give new facts, which we add to a fact database, which then produces new work, and the cycle repeats. When we get to a point where there's no more new work and no more new facts, what we arrive at is a fixed point. Writing work queue algorithms in imperative or functional languages is very hard. For example, this is Dijkstra's graph distances algorithm in Haskell. The problem is that the essence of the algorithm is hidden under lots of boilerplate. Fixed point-oriented programming makes writing work queue algorithms easy peasy. These are languages like Datalog, DataFun, Flix, Souffle, Inca, Flan, and many more. In fixed point-oriented languages, you can write an algorithm for calculating graph distances by solely expressing the essence of the algorithm, essentially by stating what the facts look like and by stating an inference rule for deriving new facts from existing facts. So our contribution is to develop a new fixed point-oriented programming language that compiles to Haskell and has two new features. The first is a generalized notion of fact subsumption, and the second is to control evaluation order via rule instance priorities. The intuition is that orders on relations induce subsumption, and orders on rule instances induce evaluation strategies. Some facts subsume others. For example, in Dijkstra's algorithm, if we find that the distance to A is 0, we don't care that finding the distance to A is also 2. We don't care, right? What we want is to care only about the shortest distances. So, in our language, relations are products over partially ordered types. We define partial orders over arguments to relations, such as by saying that a distance of 0 is better than the distance to 7. And the relations in our program automatically inherit that order. Larger facts then subsume smaller facts. For instance, if we already know that the distance to A is 0, and if we later find that the distance to A is also 2, we don't care about the new fact, since actually it doesn't add any new information. It has already been subsumed. Next, some algorithms are optimized by controlling the order of evaluation. For example, Dijkstra's algorithm is optimized by exploring the closest nodes first. What we do is to generate a work queue algorithm that uses a priority queue to store work. What is then retrieved in each iteration is the highest priority work. To control which work is of the highest priority, users can declare a rule instance priority, which are strict partial orders on rule instances. For example, we can write a declaration that prioritizes adding shorter distances first. The result is that these features allow us to faithfully implement algorithms like Dijkstra's algorithm. So to summarize, we have a new fixed point-oriented programming language where orders on relations give rise to fact subsumption, and orders on rule instances give rise to rule instance priorities and evaluation orders. So we have a white paper that describes this in a bit more detail. And lastly, I have a small call to action, which is that we don't have a name for this language. So if you have any ideas, please share some of them with us. Thank you very much.
Might I humbly suggest that to help you in your quest to name the language, we look at the boundary between what your language can do and what it cannot. For instance, what is the space of languages that can be translated into data log, and what still is work that remains to be done, you see. So you look at the limitations, the boundaries. Do you have examples of a program that is still, like that Dijkstra's algorithm?
Yep.
Yeah, but what cannot be done with the existing work?
Yeah. Oh, okay. Cool. Yeah, I think that would be a very good suggestion. Thank you very much. Yeah.
Test. Okay. Yeah, sorry. Yeah.
Introduce yourself just quickly.
Yeah. So hi everyone. My name is Kirill, and today I'm presenting some joint work with Dijkstra's over here, and our advisor is Prof. Michael Adams. And today we're presenting MiniMu, which is a language designed to explore the concepts of duality. So the key starting point of a language is that MiniMu is all about construction and destruction. So we can construct things and destruct them. So you can think of things like algebraic data types and pattern matching. But the trick is that with just this, we argue that we have a Turing-complete language. So how do we do that? So MiniMu is actually based on the mu-mu tilde calculus. something that exposes both expressions and continuations, and more importantly, exposes them in a completely symmetric way, allowing us to have a completely symmetric language. And we'll show why that's important soon. So just to describe what a program looks like in Minimu. So a program in Minimu is what we call a command. And a command has an expression on the left and a continuation on the right. And a command tells us that this expression will interact with this continuation. And to talk about continuations, first off, we argue that let in our language is nothing more than a continuation. Why is that? Because let expects some expression and continues with its body next, which is also a command. So the program steps to a different command, and that's how the program progresses. But because it's a dual language, it tells us that we have the ability to swap both of these things and put them in each other's position. And what we discover is that this allows us to create the let CC abstraction. And the let CC abstraction is dual, right? So if let expected an expression, let CC expects a continuation. So earlier I talked about pattern matching and the like. So pattern matching in Minimu looks really similar. So we have expressions which are data values, and we deconstruct them with matching on the continuation side. But again, it's dual, which means that we can have something like a pattern matching expression with some constructed continuation. And this in Minimu is exactly the difference between data and codata. So data values are something much more understood. We construct values and we destruct them in our continuation. But codata tells us that I am a value and I will respond in these ways to whatever observations you give me on the continuation side. And just now I talked about Turing complete, and why we argue that it is because functions are nothing more than codata. And why is a function a codata? Functions tell us that I am going to take this value that you give me, and I'm going to do something to it, and pass it to some continuation. What is that continuation? It is exactly the continuation that you supply us with. And it's the exact same as it is in normal programming languages, except that now continuations are made explicit. So, cool, nice and all. Let's start the program in this language. So, for example, let's see what a quicksort looks like in our language. And from this, I'm pretty sure something that becomes very apparent is that with just commands, the language is very painful to use, which is why we talk about making Minimu ergonomic, where we supply different syntactic sugar that are more familiar, that's more easy to use, in order to make Minimu fun and nice to use. And one of these synthetic sugar is what we call the cutlet style. So earlier we were talking about the let continuation. So if let x something is a continuation, then let x equals e is supplying that continuation with an expression. It's just a command. Similarly for match, if matching is a continuation, match e is exactly a command. So in this way, we hide the syntax of a command behind something more familiar. And from that example earlier, this is the same example done in cutlet style. And it looks almost like OCaml, but there's a catch. This code is wrong. Why is that? List split and quicksort both expect continuations. But where are we getting those continuations from? So if you see the desugaring of let x, if you see the desugaring of let, we observe that the entire rest of the program is the continuation to list split. And we have let cc. So all we need to do is introduce a let cc to capture that continuation and pass it to the values like so. And because we're dual, again, if we invert everything, we get a perfectly dual program as well. So, in conclusion, Minimu is a language that's fun, that's cool, because it makes things that are meant to be dual, syntactically dual. And we are continuing to explore different ways to make Minimu easier to use and more fun to use. Yeah, thank you.
We have time for one question as we transition.
Have you thought about adding types to the language? And if you did, how are the types going to be like?
That's a good question. So for Minimu specifically, we have decided to keep it untyped for now. But we have explored typing in subsets of the language. So if you think of, for example, expressions and continuations, right? We've realized that types are actually kind of polarized in the language. So in order to have a well-formed command, you must have an expression of, for example, integer plus, which is an integer expression, and a continuation of integer minus, which is an integer continuation. Yeah.
Thank you. Let's give him another hand.
Hi, good afternoon, everyone. Thank you for attending my talk. So I'll be my name is Brian, and my advisor is also Michael. So today I'll be presenting on my work on relating LL traces and LR traces. So it turns out that LR is actually an abstract interpretation of LL. So parsing is a core process in compilers. And so given a grammar and a string as input, we'll try to form a parse tree to see whether the string is in the language of that grammar. But different parsing styles or parsing algorithms explore this tree in different ways. For example, top-down LL will try to expand and predict from the start symbol, while LR tries to shift symbols until it can reduce them into non-terminals. But at the end of the day, they still pass the same parse tree. So why is it that their mechanisms are so different? Well, it turns out that there is a connection between them. So LL abstracts into LR. But you might be thinking, why do we even bother with this? You know, LR is the strongest deterministic parser that we do have. But there are a few caveats with LR. Firstly, it's very difficult to understand. If you've ever looked at the state diagram of an LR parser, it's horrendous. And this also gives rise to bad parse errors. So this will be an example of an LR parse error. It just says like unexpected in, expecting a statement. And this doesn't give the user any context. Even if I were to give the offending line, the user will have to look at it and probably parse it in a top-down manner as humans usually do. It would be much better if you could give them context such as, oh, well, I'm trying to parse this if statement. I expected a statement, but then I found an int. This is much more human readable, and it's something that LL-style parse errors generate. So is there a way that we can, with our work on showing LR as an abstraction of LL, we can get the best of both worlds? We'll be able to use an LR parser and capitalize on its expressive power on grammars and run it until maybe there's some parse error state. And instead of generating the error message from here, we first concretize it into its corresponding LL trace, and from there we can produce much better error reporting as shown previously. So this is my work, which is the universal parsing automaton. And the way that it works is that it's a single stack-based machine where on the stack it contains parsing items. And so this is how the UPA relates to LL and LR. It kind of sits in the middle. It's a nice middle ground between the two. So what are the UPA operations? There are three main core operations. The first one, which is matching. So it basically matches a terminal and advances a bullet for a given item. And if let's say it's trying to pass a non-terminal, it will it'll add a new stack item, which is essentially like calling a call frame in a recursive descent. And once it's done passing that, it will return back. So this is actually no more than a recursive descent parser. It's just that we have a more explicit return statement. And with this, it's actually enough to weakly simulate LL. What that means is that every LL operation would have a corresponding UPA operation. So LL's expand corresponds to UPA's call. LL's consume corresponds to UPA's match. But since it's a weak simulation, there are some silent return calls that we need to do to keep LL and UPA in lockstep. But what this means is that every LL trace has a corresponding UPA trace. So from here on, we'll just be reasoning about UPA with respect to LR. So how does the UPA abstract into LR? Because we keep the stack of items, we are able to construct the viable prefix of the UPA configuration. And this viable prefix is essentially the symbols that sit on the stack of an LR parser. And from there, we can feed the symbols into the goto function of the LR parser and reproduce the corresponding LR configuration. So now that we are able to abstract multiple UPA configurations into one LR configuration, what about the reverse? We're able to do the same thing, but this one will be a bit more of an exhaustive search. So what it means is that every LR shift would correspond to a partial trace of the UPA. So it could be multiple calls followed by a match of A, and the LR's reduce of some production will be simply the return of the UPA. So what does this mean? This just means that multiple LL traces abstract into a single LR trace, and a single LR trace can be concretized into multiple LL traces. So thank you. That's the end of my talk.
We have time for one really quick question while we transition. Have you implemented this? Like
not yet.
Not
So
yet.
like what we have right now is the theoretical foundations, but the next step will be to implement a working version.
Cool.
So, hi everyone. My name is Zhiqi Chen from Institute of here. Thank you. My name is Zhiqi Chen from Institute of Science Tokyo. Today, I'd like to share with you my work on live FFO programming with titles. The motivation of our work can come from the increasing popularity of effect handlers in programming languages. They can uniformly express many computational effects such as exceptions, mutable states, and non-determinism. However, for beginners, effect handlers can sometimes difficult to understand and implement. Take state effect as an example. A beginner may easily get lost in the lambdas and continuations and wondering what the continuation K is and what the variable V and F represent. We aim to provide a better learning experience for beginners of effect handlers. To achieve this goal, we combine effect handlers with the notion of typos. Typos is a mechanism to type check and run incomplete programs. And it is available in languages such as Hazel and Agda. By incorporating this mechanism into FFO languages, we can, for instance, run an incomplete handler and see what the value of the variable and the content of the continuation are. And so far, we have formalized a calculus of effect handlers and typos by extending the core calculus of Hazel. And it is based on gradual typing, and we added an effect tracking facility found in a standard effect handler calculi. And in addition to the formalization, we also built a prototype implementation in Haskell. It shows the correct result with whole context, which means that our semantics works just as we expect. However, the result is quite verbose because the continuation is not being reduced in the current implementation. So in future work, we will build a new formalization and implementation based on a constraint-solving-based approach. This switching is because gradual typing doesn't give us the strong normalization property, and which is essential to make the evaluation safe at the presence of both effect and host. And also, we want to make the output more readable by allowing a full normalization, and we can reduce the continuation body. And finally, we aim to prove the type and effect safety in our language. In summary, we propose to make effect handlers more accessible through type hosts. Thank you very much for listening.
There we go. So hello, my name is Bryson Finkston. My advisor is Jason Heeman. And today I'll be talking to you about visualizing logic programming search with fine-grained small step semantics. So I'm going to assume some basic familiarity with logic programming. Specifically, if you know some Prolog, this should come somewhat naturally. So here we have two programs, one in Prolog, one in Minikanren, and they both express the same solution set, but what's different is the way they enumerate their answers. So Prolog, which uses a depth-first search, enumerates its answers in the order that they're in. So this is very natural and easy to reason about. However, Minikanren enumerates answers in a seemingly random way. So we start with the last one we wrote, then we go to the first, and then we do some stuff in the middle. So understanding this behavior is key to understanding your programs in Minikanren. And staring at the program for a really long time won't tell you the answer because the search is implicit within the implementation. So one way you might try to go about understanding this is with small step semantics. So that's exactly what we did. We created small step semantics for Minikanren. For the sake of time, we can't go through all of these right now, or any of them, I guess. But if you want to learn more about this, I'll be talking at the Minikanren workshop on Friday. But to understand the semantics at a high level, where basically you treat your program as a tree, and your reductions are just tree reductions. So you're stepping from a search tree to a search tree. So your program consists of goals and states, disjunctions, conjunctions, and some control operations. And your values are either failure or a stream of answers, which is basically a linked list, which is a tree. Oh, sorry. So that's the semantics. We mechanize them in PLT Redux, and so we implement them in PLT Redux so we get that mechanization for free. We also get some things like you can define judgment, so we define what a well-formed program looks like, and then we could verify some properties of our semantics, such as the reductions are deterministic, so we only step to at most one tree, and they preserve their sound semantics as well. So you'll never go from a well-formed program to a non-well-formed program. So this is the visualizer UI. On the left-hand side here is where you would input your program. So this is the program we saw on the first slide. And so you input your program, and it's just the standard core Minikanren language, and you can load up your program. And there's some nice quality of life features. So you'll see at the top, there's the step count and the name of the step. So if we keep stepping our first step, we substitute our fresh variables from our query. Some other nice things are that you can click on a node, and that will highlight in your source where that goal came from. And you can do that the other way around. So if we click on this unification here, we'll see it corresponds to that goal in the tree. And so there's so you can step through your program and you'll see it's just reducing certain subtrees. One last thing that's pretty nice, and so this is showing the interleaving behavior. Well, you can also inspect the state of your goals as you're stepping. So you can see here that this goal has a state with a substitution mapping that logic variable to the fish. So, yeah. So that's it. If you want to see the source code, that's on the left. If you want to try out the visualizer, that's on the right. Thank you.
Because we're over time, let's take questions offline.
All right, so my topic was on optimal effects via token passing, which basically, so my entire work basically comes down to like having ordered execution in parallel to unordered reduction. And execution is like something that has side effects, like I/O or something, and reduction is entirely pure. And unordered in this case means that you could then, after like having this theoretical construct, decide whether you maybe want to use something like an optimal reduction scheme or maybe even reduce it in parallel, and that's then up to you. But first let's get down, like this is done via token passing, but the first important part is how this even, like what is optimality, because actually my topic is like optimal side effects, right? So basically optimality is you combine call by need, which is a lazy evaluation strategy, with radix sharing. And then you achieve something like maximal laziness. So for example, if you have this function which takes an x and then adds some big number or something, some algorithm, then this would be evaluated twice in something like call by need in Haskell, but in something like optimal reduction strategies, this will only be evaluated once. So, and how you achieve this kind of optimality, this optimal reduction, is via interaction nets. And this is basically a graph encoding of your program, which is then reduced until you achieve some normal form. And specifically in my work, I extended this interaction net with side effects. So if you actually like write a program and translate it to this graph, it will look somewhat like this, like some huge graph. And then everything that is red can then be reduced. And actually the order does not matter, because interaction nets are like inherently unordered. And then if you want to encode a certain structure, like because side effects are supposed to be evaluated in a certain order, you have to use a different strategy. And this is where the main idea of my work comes in, which is basically that we have tokens in this network, and these tokens traverse the net in a specific order and execute all actors. And actors are these, or this is first what tokens are, because these tokens move through the net. And once they hit an actor, which is this quickly thing, it causes a side effect. And this side effect will then be somewhat like if you have a side effect called, or an action called read, then the side effect will be that something from the console is read in, like a number 42, and then the side effect happened. And then the token, which is like this blue arrow, will return as a code token, which is the red arrow. And then it will continue traversing the graph. And you can also do some different things. For example, you could say, yes, a token basically resembles a thread because every execution of an action requires a token. So if you remove this token, then you basically aborted this thread. And if you have multiple tokens, you would have multiple threads in your network that you evaluated. And you can also do different things with these. For example, you could like load different networks into your network for example, that's how I implement recursion in my implementation, because then you can basically have as a side effect something like a foreign function interface or remote procedure calls, and then load these as a side effect into your network. And the important part is that you still have this reduction, which is pure, as I said in the beginning. And in this case, for example, you have a beta reduction. I know you may not be comfortable with this layout yet, but this resembles beta reduction. You have to trust me here. And this token is at the bottom right. And this token can only continue after beta reduction happened. So basically, the reduction, the pure reduction, paves the path for the execution, which then has side effects. And how these tokens are then directed is specified by graph rewrite rules. And for example, I have like researched many different redirection rules. But for example, you could implement something like a monadic style, which looks a bit dangerous, I know. But basically, you have this rules which state how this token will be redirected if it is at certain points in your graph. And then you can also do something like a direct call by radio style, and you can do a lot of things. But all of this happens while you still have a one-step diamond property, which means that you can reduce it in any order, like you can reduce this network in any order, still have the correct execution order, and still can do something like parallelism without changing the eventual reduction steps. And then you could also have multiple tokens with some kind of fork, or you can have some join operation for threading and racing, and then you can, this is what a race would look like. But this is basically all I did. So you have like ordered token traversal happens in parallel to the unordered graph reduction, and the optimality results, or the optimality property of interaction nets, and strong confluence, which is needed for parallelism, remains. And now I did a lot more in my thesis actually, which is like proofs, type system, asynchronous partial application, and I also implemented a core calculus, so you do not need these graphs. And then I also have a lot of results, but you can find this here. Thank you.
Thank you. You have a question?
Can I suggest as a way of structuring your results that in the existing literature on interaction nets, they actually work with the pure untyped calculus. Now, and you immediately jumped into effectful actions. Perhaps an intermediate step is if you introduce constants and primitives, right, before you actually get into full-blown, this is a node representing a foreign function call.
Yes. I mean, I also have some operators, like built-in operators, but there's also not that much time. So all right.
Thank you. Thank you for your attention. We will announce the winners of the student research competition at the business meeting later this afternoon.